aerospace engineering at IIT Bombay. And I've been in IIT Bombay for the last 15 plus years. All right, so I dabble in many things, and one of the things that I do work, I like to build tools for computational science, but my current research focus is in what are known broadly as particle methods, and SPH happens to be one of them. And as I said, I'm from IIT Bombay. I always like to include this one slide because I'm really grateful to IIT Bombay. They've given me an opportunity to do the things I enjoy doing, do them well without unnecessary pressures. So I'm really grateful. This is actually the IIT Bombay campus. There's a lake. There's also a hill, so it's a really nice campus, and it's situated in Bombay, so which is great. I also want to thank the organizers for having invited me to talk to you all on this interesting method. All right, so with that done, I'll introduce to you what I'm going to talk about today. The outline of my talk is going to be like this. I'm going to talk about an introduction to SPH. Broadly, what are the goals? What are we trying to do? Then I'll get into the gory details of SPH basics, as in what does it mean when you have an SPH method? How does it actually work? And this will be at a very high level. Obviously, I'm going to skim over a lot of detail, but I'm trying to give you enough details so that you're able to understand this. And if you go back and read a paper, that you might be able to at least get a big picture understanding of it. And then I'll go on to SPH for fluids. And unfortunately here, I will not have the time to actually go into the gory details, simply because it doesn't make sense for me to sit and derive all of the equations. I'll just summarize the equations, the general approach, and again try to leave you with a broad overview of the method. And then I will spend a very small amount of time, but I will spend a little bit of time on the issues. I don't want you to go away with the impression that SPH is some kind of silver bullet for everything. There are lots of issues that need to be tackled, and which is why it's an area of active research. And finally, I'll introduce to you very briefly a tool, an open source package that I've been building with my students called PySPH, which allows you to do kind of any particle-based method, but it's largely focused on SPH right now. I'll just briefly introduce you to it so that if you're interested, you can go and check it out. And then we'll wrap it up. So it's necessarily going to be a bit of a fast-paced introduction. You'll have to bear with me. I'm hoping to have some time for questions, but if something is unclear during the session, please feel free to stop me. I can't see any of you because the screen is now full screen. You may have to speak up for me to actually pay it. I will not be able to pay attention to the chat at this point. So I'm just requesting the organizers to step in if there's something wrong. You need to let me know. All right. Okay. So what is it that we're trying to do here? The goal, especially for me, is I want to be able to solve complex fluid flows. And by complex fluid flows, I mean not academic problems where you're just interested in some idealized problem and then be able to solve it with some comfortable boundary conditions or a comfortable problem size. And the difficulty with fluid mechanics is that they are, as you all know, nonlinear. Boundary conditions can be difficult to implement. And when it comes to complex problems, moving boundaries and free surfaces become difficult to track. Of course, you've already been exposed to many methods where these can be done. And there's a great deal of research that has gone into this over the years. But what we'd like to do is to see if we can make it easier for people to do this. And we also want tools which are general purpose so that you can actually do a lot of interesting physics. And so here's a typical example. I like to show this just to capture your attention 9:30 in the morning. So here is a rendering of an SPH simulation. This thing you see here is a block of water. So it's a classic problem called the dam break problem. And in addition, we have this S, P, and H, which are just solid pieces having some different, this is water and this is some other material, maybe with wood or something like that. And what we want to see is when the water is released, how this thing flows. So, and when I say complex physics, this is what I'm trying to say. It's not really crazy complex, but at least you get the idea that it's not just a simple idealized problem, but it's going to involve multiple things, right? Like the water flowing, the water being contained in this vessel, striking some other object, those objects interacting, colliding with each other, colliding with the wall, and all of the interplay between those. So the idea is, can we do something like this with some sort of a numerical framework? And the reason I'm focusing on particle methods is that particle methods offer a possible approach. And the good things with particle methods are that the nonlinearity can be handled using a Lagrangian approach. So the nice thing is, in an SPH method, SPH methods fall under this category, is that you essentially convert the problem to a Lagrangian problem, wherein you track these particles. So which means the convective terms are no longer discretized in that sense. And therefore, you save a lot in terms of the artificial numerical dissipation introduced by the introduction of a mesh and the discretization of the advective operators of those. Boundary conditions are still hard. In fact, it's an area of research in SPH in general. But you can do them again with particle method. It's not too difficult, but there are some surprising difficulties that you may run into. But the really nice aspect about these particle methods is that moving bodies and free surfaces are almost trivial to handle, because you don't have to do anything special. You don't have a conforming mesh to deal with. Okay, and this is the big advantage with using something like a particle method. And this is what allows us to do, the kind of simulations that I just showed you at this time. So SPH is a particle-based Lagrangian method, and it was introduced in the late 70s by two people almost simultaneously. So they are both considered the creators of this method, Gingold and Monahan is considered like a father of the SPH, and Lucy. And they introduced this in the context of astrophysical gas dynamics. So you can immediately tell that this is serious stuff, as in they're not looking at they are actually looking at compressible gas dynamics. So these are a hard class of problems that hyperbolic partial differential equations, and they have used it in this context, and that's how it started. However, even though it started in this area, it has been extended very, very widely. So it's been applied to all kinds of domains ever since. And the advantage of this approach is very general purpose. Essentially, it's a continuum method. So a lot of people who start out thinking of particle methods think immediately of kinetic theory of gases. And that's not the case. It's not like the particles here are representing a molecule or an atom. They are actually continuum methods, which means you're essentially using the particles to discretize a field, a continuum field. And then you take, you apply the usual operators on those, and then you end up with the discretization of a differential equation. So you can basically apply this to any kind of PDE, and you can handle compressible fluid flows, incompressible fluid mechanics. You can do rigid body interactions like the example I showed you. You can do elastic solid dynamics. You can do fracture. You can do FSI. There are a whole host of things that you can do. And people have also applied it to, ice flow, granular flow, erosion, so it's the applicability of this is very wide. So the good things are with this method is, again, as I mentioned before, you can do moving geometries, you can do free surfaces, you can do multi-phase problems, and you can incorporate various physical interactions as well. It is a Lagrangian mesh-free method, and therefore the advantages are that you essentially convert a PDE to an ordinary differential equation, which is much easier and much more tractable. It avoids the nonlinear convective derivatives that I had explained before. It is mesh-free, so you do not need to create a mesh that is boundary conforming and things like that. You do need to create particles, but you do not need the connectivity information, and that is a big that's a big aspect, and that's a big win for these methods. As I said before, it's very general purpose, and in general, most formulations are conservative, which means if you're doing things like shock or any hyperbolic system, it will capture the shocks and things pretty well. There are issues, of course, so it's not without its disadvantages. The biggest disadvantage is, of course, have to start tracking particles. It's not like a fixed Eulerian mesh. You have to keep tracking these particles. It's not a big deal, especially not these days with the kind of computational power we have. But still, you need to keep track of those particles, and you have to think in a slightly different way. The major issue with this business of everything being Lagrangian is that there is what's called particle disorder, which means you may start with a nice uniform, mesh as in quote unquote mesh of particles, but eventually these particles will sort of move based on the local dynamics, local advection, and this ends up causing numerical issues. Okay, And this is a major problem. In fact, so there are many of the modern implementations of SPH will include certain corrections to ensure that the particles are distributed uniformly. Right? That's a very important aspect. But I just want to point this out that this is an issue. Boundary conditions, as usual, are difficult, and this is an active area of research. In fact, even recently, you'll see many papers on inlets, open boundary conditions, and things like that. We have a recent paper on this as well. But this is again, but I guess this is something that's very common in all numerical methods. Accurate boundary condition implementation is always something we're interested in looking at. It is also computationally intense. So to give you an example, if you say have a problem, say a standard problem that works really well in say a finite difference or a finite volume method, you will find that the same person programs both codes, that you will find that the SPH is going to take more computation. Simply because there's a little more work that you have to do, because you have to keep computing the nearby particles every single time. You can optimize some of these, but in the most general context, it can be computationally intense. However, it does eliminate the entire mesh generation problem. So that you've got to keep this in mind as well. So if you just take a simple problem that really works very well in a mesh-based method, I suggest you use the mesh-based approach. But if the mesh-based approach is starting to fail, that's the time when you really have to start looking at things like SPH. Okay, so the next thing is convergence, and this is a sort of bugbear for SPH in general, in that convergence can be an issue. Even though it's accurate, so in fact this is a statement you'll see some big people in the SPH community saying that it's an accurate method, but convergence is an issue. And this has to do again with particle disorder and the way in which this is formulated. So I just wanted to again point this out so that you have a balanced picture of what SPH is all about. In the same way, higher order methods is also an active area of research. But then again, this is a sort of relatively new method, and not as many people work in this area. So there's still opportunity to grow. Okay, so we'll move on to the SPH basics with that basic introduction. And we start with how we approximate a function. So this will be a little mathematical, and I hope that's okay. I'm going to keep it at a very high level. So imagine we have a function, some f of r. R is not necessarily the radius. It could be f of x. This is a one-dimensional integral. We know that this is an exact identity in mathematics, where delta is a Dirac delta distribution. Okay, so under this, we essentially have a we have an integral approximation of this, not an exact integral to represent this function f. Now, using this Dirac delta is a big pain when it comes to numerical methods. In that, it's a Dirac delta distribution. So, we can't quite do any accurate numerics with it. So, what is done is this integral is regularized, which means you introduce an approximate Dirac delta distribution, and this is called a kernel function or a smoothing function. So this is a function that is a function which has compact support and is such that it has a parameter called h, which is the size of this function. So this is a compact function here, and looks like a Gaussian, and this function is your kernel. Okay, which means at every particle, at every point r prime, you have this function. Okay. And the function has this form, which is compact, and in the limit as h tends to 0, it goes towards a Dirac delta distribution, which therefore means in principle as the mesh size, so this is in a sense a mesh size, a particle size, as this goes to 0, it recaptures this exact integral. That's the basic high level principle of how functions are approximated. So now when you come to actually discretizing this, if you take a particle, so you basically discretize the entire domain into particles, and this integral is discretized now in this form. So it becomes a summation, and f is the actual fr prime. Remember, okay? So there's an fr prime, and rb is like the r is like r prime here. wra minus rb. So we're evaluating this function at some ra, and this vb is called a volume. Okay, it's equivalent of this dr prime here. Okay, so now we have this following situation. We have a collection of particles, each having some function value frb, each having some volume, and each having some smoothing length h. This is called a smoothing length h. Now, because this function w is compact, right, which means it's 0 at some distance away from that particle, you don't need to do the summation or the integral over all particles. All you need is to do summation over a small set of particles, which is called the neighborhood of this particular particle A. So neighborhood of A, so B is a set of all particles in the neighborhood of A. Okay, so Na is the set of neighbors of particle A, and Vb is the volume of particle B. So it becomes essentially an order of n method to calculate the value of the function at every point. If you have n particles, you essentially have some small radius, some small collection of particles around that which influence that particular point. Okay, so that's how you do the particle discretization. So essentially, it's just a discretization of this integral. Now in SPH, this volume is typically written down as mass by density. Okay, so it gives us an estimate for this volume, and therefore this whole thing becomes Fa is mb by rho b, fb wab. So this is something that you'll probably see very often if you're reading an SPH paper. And this WAB is just the kernel evaluated between A and B, right? And it also implicitly has this H, which is the smoothing length of that kernel. And that's it. So with this, you're able to actually recapture smoothly any function. So here's a simple example. I'm not going to walk through the whole thing. We have, like, say, 25 points in this region, discretized. We're trying to approximate a sine curve. There's a blue curve, which you can't quite see here, but you can see it in this side. There are boundary effects here, but in the middle of this region, you see that this actually captures the sine. The red curve captures the sine curve really well. And each of these green guys is a kernel, right? So you see, look at this one particular kernel, it's basically from here to here, all right? So the sum of all of these at this point will give me this value. Sum of all of these at this point will give me this value. Okay, so in this case, our kernel is a Gaussian. But there are a whole host of different kinds of kernels that you can use. Again, the only thing that you're expecting with these kernels is that they have compact support, and in the limit h tending to 0, they go to a Dirac delta. All right, so the next step is to take derivatives, because once we can do derivatives, we can actually solve PDEs. So what we do is, if you want to take the derivative, you simply take the derivative of the kernel, right? It's a little more involved than that if you actually get down to the mathematics of this, because you have issues on the boundaries, but I'm not going to get into those details. You can find that in any reasonable reference on SPH. But the basic principle is you can take the derivatives of the kernel, so you end up with the derivative of f is simply the derivative of the kernel, again multiplied by the same sort of summation. And this summation again is over the neighbors. Now, it turns out that if you use this form, it's not even zeroth order consistent, which means even if you have a constant function, you're not going to get 0 as the gradient. Because the particles are not necessarily going to be exactly where you expect them to be. It's not like a mesh-based method where the particles are exactly on the mesh. So it turns out that with some analysis, you can easily show that a better form can be used, which is this FB minus FA form. So this is a more accurate way, which is zeroth order consistent. So in this case, even if the function is a constant, you will recapture the derivatives correctly. So this is a form that's very commonly used. So let's just quickly, based on what we've understood so far, use this to take a continuity equation and try to discretize this. And now the first thing you will notice is that we write this always in a Lagrangian form, because what we want is we want to write out the governing differential equations in a form that is Lagrangian, in a Lagrangian sense. Okay, so that I can sit on each particle and look at what's happening to the properties of each particle. Right. So if you look at this, we have d rho by dt, material derivative, is minus rho div v, and this can be written in the form, if you discretize it, for each particle to be d rho a by dt is minus rho a mb by rho b vba, which is again using this form, dot with the gradient of the kernel. And this turns out to be, and this works, for example, not just in one dimension, it will work in any number of dimensions. I'll come to that very shortly. Okay, but I just hope that you understand that this is the exact same structure that we've looked at so far. Now, I just want to again point out here that this thing is really nice because it also extends to multiple dimensions, and it's super easy to do that because our SPH interpolation kernels, those W's, are actually radial functions. We use radial functions, it becomes very easy to actually generalize this to multiple dimensions. So essentially, you replace the integrals with multidimensional integration, and derivatives again become gradients of the divergence. Okay, a trace of the gradient becomes a divergence, and then you start using Gauss divergence theorem to remove any boundary terms. And then if you write gradient of W, you can write it as, if it's a radially symmetric kernel, then you can write this as dou W by dou R into r divided by r, which is essentially the unit vector along the r, along r, when r is passed as an argument to this. And remember, this r will be essentially ra minus rb. So given two particles, it's the radial line joining those two particles. So now if you want to basically take any function in arbitrary dimensions, you can just write it out as this. And this, again, you can discretize this in terms of particles. So it's the same thing, except now it has not just x-axis, you have multiple, whatever, any number of dimensions that you have. Similarly, you can do the gradient, and that just becomes this. The divergence becomes this. You can do the curl, so on and so forth. So the nice thing with this approach is it easily extends to multiple dimensions. All right, so now that we know how we can take a differential equation and we can discretize it using the SPH method, what we look at is how a typical SPH method works. Okay, I'm trying to again get back to a big picture, 40,000 feet picture. So supposing you have some domain, you discretize the domain into particles carrying these properties, right? So if you go back to what I've been discussing so far, each particle carries some density, some mass, some velocity. So each particle essentially is carrying some property, all right? So you discretize this domain into these particles, each particle carrying some density, some mass, some velocity, some temperature, or internal energy, whatever it is that you have, and representing the appropriate physics. And now if you take a particular particle, like this blue guy here, you immediately look at the neighborhood of this, so that the compact support of all of these particles will tell me the properties at this point. And then you evaluate pairwise interactions between these particles. So you can call these source particles, and you can call these destination or target particles, whatever it is. And you discretize your right-hand side of your ordinary differential equation for each particle by simply evaluating the sum over these neighbor particles. So essentially, we have reduced some partial differential equation. So in this case, this is just continuity. We'll look at the other equations in a short while. And you essentially reduce this to some summation over the nearby neighbors, which is sufficiently accurate. All right, and that's it. And then now you have a way by which you evaluate this right-hand side for this ordinary differential equation. You have a system of ordinary differential equations that you simply solve. So that's the numerics of how this thing works. Now the obvious question arises is, how accurate is this whole process? So it turns out that you can show that if you have uniformly spaced points, the error is of order of h squared. Okay, so which means h is like a measure of your mesh size in these class of problems. But then we all know that this is a Lagrangian method, and the particles are not going to be uniformly spaced. And so particle disorder then becomes a problem. Essentially, you can think of it in one way as you have this integral of which you're taking a quadrature, and you're reducing those to a summation. And that's going to introduce a bunch of problems. So it's been shown, this is not so easy to show in that, in a single slide, but it's been shown, and there are plenty of references that will get you this, that if you really want accuracy, you require, there's an additional error term here of the form delta x by h, where delta x is a measure of the interparticle distance. And what this suggests is that there should be some sort of particle overlap. And this is the reason why, even if you looked at the picture that I showed you earlier with the sine curve that we were recapturing, you notice that the Gaussian kernel functions were overlapping. And that's the reason it actually works well. So which means that the h should be actually slightly larger than the delta x, which is the spacing between the particles. And you need to make sure, suddenly voids don't start appearing in your simulation. So ensuring some degree of particle homogeneity is an important recent trend in a lot of SPH papers. So if you look at any paper post 2012, you will find that they all introduce something which regularizes the particle distribution, especially in the context of incompressible methods. And this is the reason that it's so important. All right. So essentially, we've discussed how this method is roughly order of h squared, a second order method, how it works, the big picture. So I'll just briefly go over the SPH aspects for fluid mechanics. And I'll look at this at a very, very high level, because again, I don't want to get sucked into all the details. But maybe I'll just take a step back for a second now. Has it been okay so far? Are there any questions, any doubts at this point before we step into the fluid mechanics? Okay, so the silence I'm assuming that that means everything is fine up to this point. Okay, so if there's anything that you need clarification on, I'm happy to explain that again. All right. And please do feel free to interrupt me in between if something is not clear. Okay, fine. So we now move on to the Euler equations. Again, I'm trying to keep this at a fairly high level. So if you look at the equations, and I'm looking at it in, I'm not going to go into the gory details of how you do it in 3 dimensions. It doesn't change too much. Again, as we saw earlier, all of these techniques extend very nicely into multiple dimensions as well. So if you look at the equations, you essentially have d rho by dt. This is our continuity equation, is minus rho div v. We have the momentum equation, conservation of momentum, which is dv by dt is minus 1 by rho gradient of the pressure. Okay, and then we have the internal energy, little e. So dE by dt is minus p by rho div v. Okay, so all of these are standard equations, and so again, rho and p are density and pressure. V is the velocity. E is the internal energy, and in addition to this, we need an equation of state, which is P is gamma minus 1 rho E, and gamma is our typical polytropic gas. You get Cp by Cv in this case. All right. So these are the governing differential equations. So what I'm going to do is I'm going to jump directly to the SPH approach, so that you kind of get a sense of how these things work in SPH. So the first thing that's done is you discretize the domain into these particles. So let's look at a 1D case. And imagine you're trying to solve, say, a shock tube or some classic 1D problem with SPH. So the first step would be to discretize the domain into particles, which is straightforward. And then each of these particles, you will assign a mass based on the local density. So usually these problems are initial value problems, which means you have an initial condition and you're trying to find the solution after some time. So in this case, this picture indicates you have a bunch of these particles as these black dots here. Each of them has some property mi, rho I, and fi. Okay, and you can discretize the initial conditions ui. So u in this case would be the x component of the velocity. So ui, pi, and ei. Okay, in addition to the mass and the density, of course. And now we already have these equations. If you remember, these equations are all written in Lagrangian form. So in fact, this is the first step if you're going to think about using SPH. Is if you have your differential equations, what you're looking to do is you're looking to rewrite those differential equations first in Lagrangian form. And then you go ahead and discretize it. That's the first step. And the nice thing with this is, maybe it's prudent to spend a little bit of time on this, is if you were to look at this system, it's a system of ordinary differential equations. So if I have like one particle, I have d rho I by dt equal to this right-hand side, dvi by dt is the right-hand side, dei by dt is the right-hand side. And I've also missed one thing here, which is kind of implicit in all of this, is that dx by dt is v. Right, that's the equation that closes this entire system, right, along with the equation of state, right, which means each particle's position is now going to be moving. It's not a fixed particle, which is the reason we are able to do this Lagrangian approach in the first case. If you contrast this with, say, a finite volume method, which is very often a fixed mesh, you end up with this. You'll have to take this, you'll have to expand this out, and you'll have to deal with these convective derivatives, which we do not have to deal with. Okay, so this makes many problems a lot easier to deal with because we don't have to worry about the convective derivatives. All right, I hope that's clear. So essentially you have these particles. These particles are moving in time. You track their position by using simply dx by dt is equal to v. And now you have a bunch of ordinary differential equations. The only thing we need to do is we need to write these right-hand sides in an SPH form. Okay, so which is what we come to. And we have already seen the continuity equation, and the continuity equation can be written as d rho I by dt. So left-hand side remains pretty much the same, it's just discretized in terms of the particles, is equal to this right-hand side is your SPH approximation to the right-hand side. In this case, it's mj by rho j, vij, it's not vji, it's vij in this case because there's a minus sign outside, dot product with the gradient of the kernel. And then for the momentum equation, you have dui by dt is this. And this looks a little more complex, and there's a reason for that. Since we have a bit of time, I'll maybe explain to you why you end up with this crazy looking form. So if you notice, this is also a gradient, right? So this is just a gradient of pressure. Right? So in principle, it should have just been pi or pi minus pj into the gradient of wij. It is not in that form simply because this form lends to a conservative form, in the sense that if I were to look at the total momentum of the system, and I want to ensure that the total momentum is conserved, you will find that if you use this form, you will end up with some lack of conservation. And this is because if you take any two particles, if the force applied by one particle on the other particle, so in this equation, let's just focus on the momentum equation. If you, hang on. Oops. Okay, so if you focus on this equation, right? What we want is, we want the total momentum to be conserved. So now one way of thinking about this is, so let's say you have a system, this is the acceleration, right? This is the acceleration. And this is the net force acting on this particle I, right? So this term, you can interpret it as the net force acting on this particle I. So if you have a collection of particles, right? And if you know that the forces between between two particles is pairwise equal and opposite, then you know the net force acting on this is zero, the system as a whole, which means the whole system is not going to accelerate. And that is essentially a conservation problem. In fact, if you look at it from classical mechanics, all of these, the Lagrangian, the Hamiltonian, all of these actually, they use some of these to actually derive some of these equations. But I'm straying far afield. But the idea is, if I were able to say that the pairwise interaction between particle I and J and particle J on I is equal and opposite, then I will have a conservative form. Okay. So in SPH, you will notice that people tend to use these kind of forms simply because they will lend to this kind of a symmetry, an anti-symmetry, if you will. Right? So if you take, for example, if you just swap I and J, you will find that the expression is exactly the same of this part. So let me just clear this out. Okay, so if you look at these terms, this part, right, will be written in a form such that it is entirely symmetric, which means if I swap I and J, I will get the same expression. Okay. However, if you look at this guy, if you swap I and J on the gradient of the kernel, you can easily see that for a symmetric kernel, you take the derivative, it becomes anti-symmetric, which means it will get a minus sign if you swap the sign. And therefore, if I just ensure that this term remains symmetric, I can ensure that this whole thing is conservative. And in Euler equations, this becomes very, very important, because if the scheme is not conservative, you will probably not be able to capture the shocks correctly. And that's the reason you will start seeing these kind of forms. It's not very hard to derive this. It actually comes from a simple vector identity. And you can apply that and get this. So, and this is very standard. So if you read any literature, I'm going to give some references at the end, you'll easily see how to derive this. All right. So we also have an equation for the internal energy, and you can write it out in this form. Again, it's motivated by the same principles. And those of you who are alert this early in the morning will notice there's this funny term that I've introduced here. This funny term is actually the artificial viscosity. And this again, some people will look at this as a defect of the SPH method, in that an artificial viscosity is considered, an old-fashioned way of solving this problem. But because of the way in which SPH is formulated, it's a lot more convenient to do it in the form of a artificial viscosity. However, there are Riemann-based SPH schemes also, but unfortunately, I'm not going to introduce those at this point, because that kind of goes a little too far afield. Okay, so this artificial viscosity term essentially stabilizes this scheme when you have shocks, and that's what this term is. I'll show you how the form looks in a little while. But I want to point out one important thing in SPH is that if you look at a typical paper in SPH, you may not see the equations in exactly this form. And this is where it starts getting a little difficult with an SPH, with the SPH literature, and that different people will use different kinds of approaches and different schemes. So there are many different forms of the equations. I'll share this reference with you, and many of the original references will sort of go into the details of why they use a particular form or not. And the artificial viscosity itself looks something like this. It looks a bit complicated, but again, if you read the references, you'll realize that it's actually trying to mimic real viscosity. So this is the artificial viscosity term. So you add it into this, and then you can just discretize a problem, solve it as a system of ordinary differential equations, and you'll end up with a solution to the Euler equations. So I'll quickly move on to incompressible free surface problems, which is where you would find a lot of modern work goes on in this particular area, simply because free surface problems are much easier to deal with in the SPH context. Now, again, there are many flavors of how you can do the incompressible solvers. For example, there are fully incompressible SPH based approaches, but that again is going to take us away from the big picture overview I'm trying to present here. So I'm only going to look at what are called weakly compressible SPH formulations. And these, this whole class of SPH schemes was first proposed by Monahan again in '94 in his JCP paper. And the approach that he uses is to basically make the fluid slightly compressible. So the idea is using all the experience that is gained in using SPH for hyperbolic problems, you essentially make this a weakly compressible problem and solve it in that sense. So if you look at, say, water, the speed of sound is like 1,500 meters per second, right? And this would require that the time step will be very, very small, right? If you're using an explicit time stepper, which is usually the case in SPH, your time step then becomes restricted to the order of h, which is your particle size, divided by c, which means your time steps are going to be ridiculously small. And so what Monahan did was he essentially introduced an artificial sound speed and made it about 10 times the maximum velocity of the fluid flow. What this does is it essentially gives you a Mach number 0.1 flow, which is like not really too compressible. And then he proposed a different equation of state, not the traditional equation of state, and put those together and use the same hyperbolic approaches to solve this problem. Okay? And to deal with free surfaces, especially the original proposal, there was no special treatment made for the free surface, right? So it just is naturally captured by the moving particles themselves. So the equations look like this. You have the continuity equation, which is the same old equation, nothing changes. Then you have the momentum equation, which again looks exactly the same. If you have viscosity, you'll have additional terms as well. But I'm not going to go into those at this point. And then you have this equation of state, which is often called the Tate equation of state. But now if you look at any standard fluid mechanics book, this is like a fairly standard equation for, say, water, right? And in this equation, rho naught is a reference density, gamma is typically 7 or 1, and chi is some background pressure, and very often it's set to 0. And again, you have the same kind of an artificial viscosity, again, used in this case. Depending on the paper, depending on the specifics of the scheme, they may or may not use this artificial viscosity, but this is a typical form. So again, notice that it's very, very similar to what we've seen before. And again, notice there's no energy equation because it decouples in the incompressible case. So the next big question is, okay, we've done all this, we have all these equations. If we just step back a second, again, it's the same process, right? You have a set of particles, whether it's 2 dimensions, 3 dimensions, or whatever it is. You discretize these particles, you set some properties of these particles, and then you solve these set of ordinary differential equations, and boom, you have your simulation. Okay. Well, it's always sounds nice in theory. In practice, there's obviously issues that you need to be careful about. And one of those is the solid wall boundary condition. So if you now have a wall, how do you deal with the wall? So it turns out, again, in SPH, there are many ways of dealing with solid walls. One way is to use what are called ghost particles. Another way is called a repulsive force. And then there are another approach called dynamic particles. I'll explain some of these. So in the ghost particle approach, it's fairly straightforward, as in, if you have a wall here, so imagine this is your domain, you have some fluid and you have some solid region. A ghost particle approach will essentially take, for every fluid particle in this neighborhood, it will mirror those particles and introduce new fictitious particles in this. Okay. Again, kind of standard. The repulsive force approach is essentially you put a bunch of particles in a fixed location to represent your walls, and then you add some kind of a Lennard-Jones-like potential, which basically means if a particle comes too close, it will impose a force on that particle and move that particle. However, I tend to prefer this dynamic approach better. And what that is, it's a very simple way to implement boundary conditions. I'll talk about that briefly in the next one, which is, the idea is you treat the solid as if it is a fluid. You keep the particles fixed. You keep the particles fixed. Right? So you basically, if your solid is here, you discretize these solid fellows into these solid particles. You have the fluid particles. And now for these solids, you basically solve a sort of density for those particles, and then you set the pressure of those. So maybe I should explain this a little better, but I'm running a bit short of time. The idea is you set the pressure of these particles and use the pressure to drive the fluid particles away. So if you know the fluid particles come close to the wall, essentially the density is going to increase. That's going to cause a rise in pressure. It's going to push back the fluid particles. So the idea is you essentially treat the solid also like a sort of fluid, and you allow them to just interact as if they are two fluids. And therefore, the fluid particles can interact through either a continuity equation or a momentum equation. So you can apply, no tangency boundary conditions. You can apply no slip boundary conditions and things like that very easily with this sort of a method. And the nice thing is, because the solid is again just discretized with a fixed set of particles, you can just take whatever surface that you have, discretize it into particles, and in principle be able to apply the boundary conditions. So this is how you can apply boundary conditions. And using this, now we have put together the whole thing, right? We have the partial differential equation. We have the discretization technique. We know how we can take this PDE and convert it into an ODE, system of ODEs. And then we now know how to do boundary conditions. So now we are in principle good to go to solve a whole bunch of problems. So what I'll do now is I'll switch to showing you some example simulations just to give you a flavor of the kind of things that you can do. So here's an example of a free surface problem. Again, it's a water in a glass. You can see the splash and all of those things are just naturally captured. This simulation actually was made with a incompressible SPH solver, which we have developed. But yeah, I just want to show you that, yeah, so the free surface capturing is just completely natural. We don't have to do anything really special in this case. And you can do something with an older simulation of a boat. Again, this is not like this is just a pretty picture simulation. It's not really an accurate one. Just to show you that, you can have these complex things happening in this case. We can do gas dynamics as well. This is just a standard example in our software, which you can run. It's just a shock tube, solid shock tube, but there are a whole host of, you can do blast wave. All of those can be actually solved. Again, this is compressible gas dynamics. There's a standard shock tube example, right? You have a low density gas and a high density gas separated by a diaphragm. You explode it and then look at the waves. So this is that. You can do compressible gas dynamics like this kind of instability problems as well. This is again a fairly recent paper, 2017 paper, which we have implemented in our open source framework that you can use. You can also do elastic dynamics. So this is something interesting. There's two steel rings that are going to collide, and you can actually look at the elastic dynamics of those. So all of these can be done with SPH. Again, it's exactly the same approach. The details of how you do the PDE, how you discretize it accurately is the thing that really changes in this case. All right, so we have about 15 minutes, so I'll just quickly try to wrap up. So what are the outstanding issues? Again, I have only one slide on this. I'm going to spend some time talking about this. As I said before, one of the big issues is particle disorder. So this is a massive problem simply because your accuracy kind of relies on having reasonably uniform particles. And so when you start having particle disorder, a lot of the techniques fail. So there are a bunch of corrections which allow you to work around these and to get an accurate discretization of your fields, even in the presence of slightly disordered particles. The problem though is when the instant you do a correction of that kind, it ends up making the system of equations non-conservative. And this is generally a big no-no. Especially if you have compressible flows. But even if you do not, conservation is something that's generally highly valued in SPH. In fact, that's ascribed as one of the big reasons why it was very successful in the astrophysics domain. Now, so therefore, there's this sort of balance between requiring convergence or requiring higher order or good order of accuracy in terms of convergence properties. And there is the contrasting requirement that, look, I need particle disorder to be dealt with. And there's also, in the whole mix of this, there's also convergence. So essentially, there's convergence and there's also conservation. These two issues, the interplay of these and finding the right balance between these is difficult. So this looks like one of the major challenges that is currently a lot of folks are looking at in terms of resolving these. These are all current issues. So getting higher order convergence, for example, or even proper second order is generally something you will not see too often. If you need to do this, you need to do a bunch of things which don't kind of make too much sense in terms of a computational implementation. And again, this whole issue of conservation is something that's very valued, obviously, but it makes doing some of these a little harder than we would like. And thrown into the mix of all of this is the fact that if I want to get more accuracy, it looks like you need more and more neighbors. But if you instantly have more and more neighbors, your computation becomes more and more intense, which means I have to do more computations just to make my simulation more accurate. And that is a no-no, because if you want to scale this up and you want to get good accuracy or good convergence properties, it means that the simulation is going to get slower. So this is also an issue that people are generally working on. And then doing adaptive resolution, even though you might think, oh, it's like, oh, should be easy with just particles. It's not. In fact, it's an area of active research. Because managing the accuracy in the context of the disorder that the adaptive resolution introduces, in the context of any diffusive effects that it introduces, is a tricky business. And so there are some papers, but it's also a lot more sophisticated to implement these things. And therefore, these are active areas of research. So SPH is really nice. In fact, you do a search on the papers of SPH, a huge number of methods, huge number of applications, but it's not without its problems, okay? Which is why it makes it interesting for us. All right, so I'll wrap up finally with an introduction to PySPH, which is a framework that I've been building over the last, 10 years. It basically provides common infrastructure needed for general particle methods. But our focus has been on SPH, so the name is basically a holdover from that. But in principle, a whole host of meshless particle methods can be easily implemented in this framework. It's open source, it's available on GitHub, and that's the URL. And so I'll just quickly go over the features. It's fully open source. It's a high performance code, and it will work on multi-core CPUs as well as on GPUs. And it also has built-in support for execution on a distributed cluster. And the nice thing about this framework is it's designed to be reasonably user-friendly, in that you can write your interparticle interactions, your integrators, and all of those in pure Python, which means you don't have to write any low-level code at all. And then the framework will automatically take that high-level description of your interactions and generate high-performance code for you on the back, in the back end. And we will use OpenMP for multi-core. We can use MP. We can use either OpenCL or CUDA for GPGPUs. And this whole thing is completely cross-platform, so it will work on Windows, Mac, and Linux. And it supports a whole host of different SPH schemes. We can do compressible SPH, weakly compressible SPH, incompressible, shallow water SPH. There's some basic elastic dynamics as well. Even some plastic elastic equations are in place. But a lot of these really require someone to spend time with them. So some of them may be in different levels of maturity, but all of them are fully open source. And the software itself is BSD licensed. As I said, it's hosted on GitHub. We have extensive documentation fully available online. It's called pysph.readthedocs.io. You can check the docs. It's installable, it's cross-platform, and we try to follow some good software development practices. So we write unit and integration tests. We have continuous integration testing on a bunch of these online services. So we try to do a good job maintaining the software. It's hard work. And how you use it is as follows. So if you wanted to say, run say lid-driven cavity, you would write a single Python file, and then you can say Python cavity.py. You can run it with -h. It will give you a bunch of options. You can specify command line arguments. But then if you want to run it, say, on multiple cores, you can just say --OpenMP. It will actually use all the cores. You can then run it on MPI if you want. Obviously, tiny problems will not scale very well on MPI. But if you have a huge problem and you want to scale it up, you don't have to change your code at all. You basically just run it on MPI. It will actually figure out the details and do that for you. And you could also run it on a GPU. Although, again, what performance you get really depends on the nature of the problem, so on and so forth. Now, in terms of the usage, as I said, the user writes pure Python code. and PySPH will generate high performance code, and the same code can be used in serial or parallel. And it also features this really nice or handy, not really nice, a handy user interface to visualize your results with PySPH. And it ships with about 90 plus built-in examples. Each of these examples are reusable, in that when you install the package, you can sort of import those examples and modify bits and pieces of those. They're self-contained. Very often they compare with exact and experimental results. So again, I'll summarize because we're running short of time here. Provided a very broad overview of SPH, which is applied broadly to fluids. And I've introduced PySPH very, very briefly. And here are some references which I can share with you later as well. If you're interested in PySPH, here's the documentation. And I will stop here. Thank you very much.
Thank you very much for a very, very interesting and enlightening talk, Dr. Ramachandran.
Welcome.
I have a couple of questions.
Please.
One is there a course on this available on NPTEL?
Unfortunately, I don't think so. I think the only course in the country is a course I offer in campus.
Yes. If you consider putting it on NPTEL, it will be very helpful.
The only thing is it's a lot of work. So, so there's I actually have some online material. This last year, I converted it to online lectures.
Okay.
And yeah, those are available, but it's kind of very focused on SPH, not a full course. And it's more designed to a course curriculum kind of thing. It's not like a very general workshop series.
Okay.
But I totally agree. I think I should maybe at least, even if I don't make it an NPTEL course, I should maybe make a YouTube series or something.
Yeah, a YouTube series would be next best kind of thing.
Yeah. So the only problem here is, if you get into the gory details of SPH, it's very easy to start making like very serious boo-boos, in the sense that there are some big names in this area. Right?
Yes.
And if I'm offering a course, I got to be really super careful. Somebody looks at it and says, "Hey, that's wrong" or whatever. So
well, that's good.
Yeah, no, it's fine. It should be done, because there are some reasonable books. For example, for a basic introduction, Liu's book is pretty good, but there's a more mathematically inclined book by Liu, which is really nice. And Monahan's papers, his review papers, are also very nice, because especially if you're already familiar with the math and the basic math and the other numerical methods, it's actually not too difficult.
Okay. My next question is, when you do post-processing, let's say using VTK or something like that, VTK, or rather your Mayavi based on VTK, whatever, it expects a gridded data, right? Or a mesh data.
Yeah.
So you normally interpolate to a mesh before you do your plots and contours and animations?
So that depends. So if we are looking at just property values, yes. In fact, we provide a small interpolator class which will do an SPH or a Shepherd interpolation or a higher order interpolation on any query points. So you could use that to do a visualization. So typically that's what we do. But if you're looking at, say, problems where you're looking at SPH results, very often they're interested only in the nodal values. So you look at the actual nodal values, but then again, that has no meaning because the point can be anywhere.
Yes.
So very often, if you're looking at a specific set of points, you will have to interpolate with something. But for the animations that I generated of the those surfaces,
yes,
very often they're just rendered with the particles. But in my case, I actually do a triangulation.
Okay.
In fact, that's something that's a paper that's currently still under the works. So I have something where I generate a very rapid triangulation.
I mean, I guess we could do a Delaunay kind of triangulation or tetrahedralization to
yeah, but it's very expensive, and to do that fast in parallel is kind of hard. That's a whole problem in itself, which is what yeah.
Now my third question is, if I like to use SPH for let us say open channel flows, which are characterized by turbulence and rough walls specifically. how would we go about using turbulence models, especially in conjunction with rough wall treatments?
Yeah, so to be honest, I have not looked at anything in the rough wall area. But in terms of general turbulence, I have noticed that people do have like LES based models, and some sort of models are there. The only problem is it's SPH is a smaller community, and in which there's an even smaller community looking at this. So this is one area which I'm looking to get into a little bit. But it's not too well explored. In that there are a few things, but you will not find as much literature on this as you will find, say, in anything in the finite volume or finite difference. That is again an open area. So, but definitely you can do. People do have Smagorinsky models. I've seen, in fact, some of the other open source tools also have some implementations of those. But it's a matter of, as with a lot of these turbulence models, it's a matter of actually testing it out for various problems before you can actually say anything. So yes, it can be done. It is doable. It's just an area again, which is a nice open area for research. That's a nice thing about this area. So everything you ask is basically possibly a research topic.
Yes.
Yeah.
Yes, and especially notice in the context of shallow water, since you would really probably like to include some kind of friction factor kind of approach for the bottom friction. And
so they do the same Manning corrections that are usually employed in so they actually have surface roughness implemented in shallow water. So shallow water equations, they do include some of those walls.
Okay.
But there it's like just one more term that you add in the bottom layer, which is so you can any bathymetry can be handled. And in fact, yeah. So in terms of the numerics, they can do all kinds of things. You can have Riemann-based solvers. You can do all of those things.
Okay.
But yeah, turbulence is one area where I'm not quite sure. I honestly am not sure of the state of the art, and I don't believe there is anything near at the level of advancement that is there in the finite volume community. I think there's definitely an area of research. But yes, in shallow water equation, people do use the same standard things.
Okay, great.
Yeah.
Hello, Prabhu. It's me, Murali here. I have one question. Hello. I just want to know whether your PyMesh, your PySPH includes a capability to handle, say, two-phase flows like air and water by introducing, say, colored particles. You have one color for air, one for water. Right. And have you done that? I mean,
so there is one student had looked at this, but it was sort of preliminary. There's another student who's actually more aggressively looking at it now.
Okay. Yeah.
The problem with the SPH is once you have the framework, the rest is just those equations, right? Those discretizations you can do. So that is trivial to write in PySPH. So that any kind of formulation you can just if once you know the framework, it's like a matter of half a day to write it. The difficulty, of course, is making sure that formulation is right is a lot of work, and that requires testing and the usual dedication and what's the word I'm looking for? The details. You're paying attention to the details of these numerics, and the physics modeling is. If someone is willing to put in that time, it's not hard to actually do. So there are, in principle, yes, we could do any of those problems. It's just a matter of those equations, and we are working on some of those. So I can't tell you, okay, just use this and boom, it will work automatically.
Okay.
So the way in which we've built the framework is that it's a tool that allows you to explore pretty much anything. In fact, we can do adaptive resolution, a whole host of these things we can do. But it's a matter of so we have not had someone who's actually solved some nasty standard problems and that we can assert, okay, this is going to work. I do know that there are people who have used PySPH for specifically these multi-phase problems. There are some recent papers where they've used PySPH to explore different models. For example, Tartakovsky has a model, and in one of their papers, a couple of their papers, Erin Arai et al., they have used PySPH actually for this.
Okay, thank you. I just wanted to follow.
Good morning, Professor Prabhuji.
Yes.
You opened a very good topic since we always tend to go towards finite volume method and then capturing shocks in compressible fluid. Actually, I am from NPCL, and we always look for a problem associated with the hydrogen detonation and capturing good shock in that case. So I think somebody must have worked on the SPS with respect to such types of problems.
Yeah.
Can you throw some light on that?
Sure. So, I mean, in fact, if you look at all astrophysics problems, they are really tough gas dynamics problems, right? A lot of them will have these massive shocks. For them, angular momentum conservation matters, linear conservation matters a lot because they need to really capture those shocks and those expansions. So there's a huge amount of literature actually in the astrophysics. In fact, they drive a lot of the innovations in this method. And it has been used. It has been used for detonations. It has been used for underwater detonations. It's been used for, even the shell casing explosions. People have actually done things with SPH in that area. So yes, it's definitely, it has applications in those areas. And the nice thing is because it's sort of multidimensional easily, and you can have these, if you don't have boundaries, in the astrophysics, the nice thing is they don't have any boundaries. And they also incorporate gravitational interaction. So all of those are actually doable in SPH. Although in astrophysics, folks are moving more towards moving cell methods. There are also sort of SPH-like approaches that work on top of an SPH framework to simulate these problems. So there are some recent papers. So if you look at the work of Hopkins and Caltech, a lot of he has a new family of schemes which are Lagrangian, but allow you to capture shocks and things like that. So yes, it's certainly an area which can be done. So there are Riemann-based solvers, there are the standard set of SPH solvers. All of them are certainly available, and yeah, they can do a good job. Because, for example, many of the finite volume-based approaches, if you have a mesh, right, you'll find that if you have a problem that's not aligned to the mesh, you'll start having dissipation between those. Those kind of issues do not happen with SPH. However, you may have other issues, right, because of the particle disorder and the whole host of other numerical issues. But it has been applied extensively in astrophysics for these specific kind of problems.
I think that software which you are talking about maybe having some cases with respect to such type of analysis.
Yeah. So, for example, if you look at there's Gadget, there is Gizmo. All of these are sort of open source available packages, which will have a bunch of these cases. Even PySPH has a whole bunch of these, explosion cases. There's NOS implosion test, CDOP blast wave. All of these are available. They're standard problems that are available in most of these tools. Whereas those bigger tools, the astrophysics guys will always be concerned with, they'll have a gravitational component, which is a big problem, n-body interactions. So that will also be available in some of those codes.
Thank you, sir.
Yeah. So let us thank Professor Prabhu Ramachandran for his talk on SPH method in fluid mechanics. It was a really nice talk, and he has given presentation on some new method in looking at solving CFD kind of problems. May I now request Dr. Manas Das to present on CFD simulations of Magnetorheological finishing processes.
Okay.
Dr. Manas Das, please.
Yeah, so I'm sharing my PPT now. Just 1 minute.
Yeah, thank you, everyone. See you later.
Yeah, welcome, sir.
So, Dr. Sumer, is it visible?
Yeah, it's visible. Can you make it full screen, sir?
Yeah. Okay, I think it is visible.
Yeah, it's visible, but please make it full screen.
No, I made full screen here.
Can you do one thing? When you present, that time you click on full screen first.
Okay, I'm sharing again. I think there was some problem.
In the bottom, there will be near turn on caption, raise hand, there will be present now option. In the present now option, you click on your entire screen.
Okay, entire screen.
Yeah, first option.
Okay.
So now your screen is should be shared. So yeah, you start, click on presentation and then F5.
No.
Yeah. Yeah, now F5. And you can hide this bar. Yeah, click on hide. Click on hide.
So
Yeah,
it is
thanks.
visible now.
Yeah, yeah.
Okay, so thank you, Professor Sumir Dirgure, for giving me opportunity for this talk.
Excuse me, I think there is the little typographical error in that. Dr. B.R. Ambedkar is just NIT Calicut.
Oh, sorry. Actually,
You can
okay.
remove this just line. Thanks.
Okay.
Thank you.
Okay, so thank you, Professor Sumir, for giving me opportunity for this FDP on modern computational fluid dynamics, CFD, with industrial and environmental applications. From NIT Calicut, Kerala. And good morning to all the faculty members and scientists and students. So I'm going to talk on this CFD simulations of magnetorheological finishing process. So first few minutes actually I shall discuss about that what is magnetorheological finishing process. So I want to tell that actually I'm not from actually fluid thermal background. So although I have done some of my work, actually part of my work in this area in magnetorheological finishing, and I have done actually some simulation work there. So actually that work actually I'm going to present here. So first actually how actually we are making this magnetorheological finishing process, how we are making this ingenious developing this fluid, this is a smart fluid, and how it is useful for our actually for the finishing process. That actually discuss first. So it will be little bit different than actually whatever means it is little bit actually in manufacturing oriented. So that's why some setup, all these things actually a little bit I shall discuss before starting on my actually original simulation work. So this is the actually my outline of my presentation. So first I shall discuss about the demand fluid synthesis and characterization and different experimental setup, MRF, MRF, RMRF, magnetic field assisted finishing and finishing of prosthetic implants, and then CFD simulation of MRF process I shall discuss. Okay, so these are the different advanced finishing process, why it is required, because nowadays most of the finishing process actually they need actual complex geometrical shapes, and controlling the finishing forces it is very difficult like in conventional finishing process, and we need actually finishing in the angstrom, nanometer, angstrom level, and most of the workpieces mainly actually it is complex freeform surfaces. So and we want to automate all the finishing process. So conventional finishing process like honing, lapping, and grinding, these are actually not suitable, and so that's why actually this advanced finishing process has developed. So these are the different surfaces like this investment milk parts, aerofoil, then turbo components. So these surfaces it is very difficult by some grinding on honing or lapping process like medical equipments, and this kind of bent tubes are there, internal surface of bent tubes, miniature gears, hard valves, and then exhaust manifold. So these parts are actually welded together, and then at this junction actually if it is not properly polished, so there is a fluid flow path will be disturbed there. So injector nozzles, so here you can see here this kind of holes are there, there may be some bars may be there, that bars actually it should be removed properly. And nowadays you know that actually lots of prosthetic parts are there like this kind of knee joints. So over age, actually, due to the means less fluid, actually this friction actually it increases, and that's why actually these debris particles accumulate here. So that part actually it is removed, and it is made of cobalt chromium alloy or a titanium alloy. This pivotal component, it is placed there, and this is the ultra high molecular weight polymer. So it is placed here, and this is the tibial component. So this part actually, this knee joint part, it is totally replaced. So polishing this kind of product actually it is very much required. So these are the few for polishing techniques which are advanced polishing techniques which are actually available nowadays. So this Magnetorheological finishing process, it is used extensively in industry. There are dedicated machines are there actually for that. And these Magnetorheological finishing process, it is used for polishing lenses and mirrors. Okay, so in missiles. This requirement is actually in the angstrom level. So that's why actually this kind of advanced finishing processes has come up. So this just I'm giving some description of this kind of AFM process here. You can see this kind of viscoelastic is there. So this medium, it is mixed with abrasive particles. So there are two pistons are there. That is a hydraulic unit. So using that hydraulic unit, this kind of reciprocating motion is given, and when this fluid actually passes through this restricted zone where we need finishing, actually we are actually in that places actually it is polished. So this kind of viscoelastic media development is actually very much important. So Extrude Hone is the company where they develop this kind of media. And, so this media is resilient enough. Actually, it will take the shape of the work workpiece immediately. So it is very any kind of complex shapes it can immediately take the shape, and it can hold the abrasive particles. So any of the when this media actually flows through this restricted zone, then only it polishes as the abrasive particles are mixed with that. So these abrasive particles also so it polishes the surface, it removes the surface undulations. So this is the Magnetorheological finishing process. You can see here. Here, this is the mirror here. So lens, actually this kind of complex lens, convex, concave, any kind of lenses, actually it is polished by Magnetorheological fluid. So MR fluid, it is actually smart fluid. Here, so first actually I'm going to show how it works. It contains this kind of actually some base media. So this base media, it may be water-based media. If it is water-based media, people use actually deionized water, and if it is oil-based media, then people use actually mineral oil. So it can be silicone oil or paraffin oil. This kind of oil actually it uses, and then they in that base media. It is around actually 40 to 60% is the base media. Okay, so in this base media they mix these iron particles here. So these are the carbonylene iron particles. So it is FeCO5 iron pentacarbonyl. So this carbon iron particle, its remnant magnetization is very less. So it is if you remove the magnetic field, then immediately it is demagnetized. So remnant magnetization is less here. And now whenever you are applying certain kind of magnetic field here, so suppose it is the north and south pole here, then what happens actually along this magnetic line, suppose these CIP particles actually make this kind of chains. So these CIP particles makes this kind of chains along the magnetic lines of force, and as well as actually abrasive particles are also mixed. So these abrasive particles, it is in random in size, and it has many random cutting edges are there. And then these abrasive particles actually it is getting held in between these CIP particles. So when it is held in between these CIP particles, it removes the surface undulations from the workpiece surface. It removes surface undulations from the workpiece surface. So bonding force is actually required. Like in metal cutting operation, you know, for holding purpose, actually there is a tool post is there. So whatever this cutting force, thrust force, it comes from that, and that tool force should give that kind of actually force actually it should resist. So in this case also, that kind of forces actually it is given by this CIP particle chain. So it is surrounding. So it is surrounded by abrasive particles. So all these abrasive particles are actually surrounded by CIP chains. So these CIP chains are actually not continuous because these abrasive particles are non-magnetic here, and CIP particles only there. These are ferromagnetic particles. So whenever some abrasive particles comes, non-magnetic abrasive particle comes, this CIP chain structure actually breaks. And after that, immediately after that, another chain structure comes. So if you are flowing this media through a cylinder or whatever, so at this zone only where you are applying magnetic field, at this zone it becomes actually non-Newtonian. But without application of magnetic field, this fluid behaves perfectly as Newtonian fluid. So you can see here these CIP particles and abrasive particles are actually randomly distributed. But whenever you are applying magnetic field, it becomes actually a non-Newtonian fluid. Now, if you are flowing this fluid through some pressure gradient, then at that time actually you have to break the chains. So for breaking the chains, actually you have to for flowing the fluid, you have to break the chains. Otherwise, actually these chains resist to flow to allow the flow of media. Okay, so the with this actually the introduction, what happens actually this in this case, what happens actually this the magnetic field where they are applying means in this zone only. This is the finishing zone only. So there is a disk is there. Through this disk, actually this media flows through this disk, and it is rotating about this axis, this disk, and this is the workpiece holder. It is also rotating in the opposite direction. And so like this, actually this entire surface of the workpiece actually it is polished. So this is actually it is developed this Magnetorheological finishing techniques. It is developed by Center for Optics Manufacturing Rochester in USA, and their different models are there, QD technologies. So our this BRC and BRDO, these people, they are trying to get one of their machine actually for polishing of this kind of lenses, but because of this actually it is used in defense purpose, they have not supplied yet. Not a single machine is available in India. So that's why actually we have developed, we have tried to develop some certain setup here. So this is one of the setup what we have so this is actually their QD technology, their main setup is there. So this is the drum over which actually there is a ribbon, polishing fluid ribbon is there. So a marked fluid ribbon through a nozzle actually it is delivered over the drum. This disc actually it is a part of a sphere. So it is made part of a sphere because actually they need a point contact here. And then there is a pump, peristaltic pump. Actually, through this pump, through this nozzle, actually this MR fluid is delivered like a ribbon over there. And then there is actually suction nozzle is there, suction pump. Then it comes to a actually MR fluid conditioner where this MR fluid rheological property is maintained and temperature of the fluid is maintained. Like that actually it works, and in this zone only magnetic field is applied. You can see here north and south pole here, and magnetic field is this north and south pole core material is designed in such a way that actually magnetic field is actually concentrated here only, where they are getting this pollution, and this kind of dwelling motion is given, and it is also rotated about this axis. So this disc is rotated along with this ribbon is rotated. So you can see here actually this kind of zone is generated. So this fluid, it is passing over the disc from right to left. Here you can see magnetic field is applied along this direction. So chain structure are forming like this in the perpendicular direction. So this is the convex lens here, which is rotating, and as well as certain kind of dwelling motion is there. So this fluid is actually sheared, and here this small spot actually it is generated. Very small spot is generated. And because of the shearing only, actually this finishing occurs here in this case in the MRF process. So what we have done actually, we have developed this kind of experimental setup actually mimicking their MRF process. And I already told this abrasive flow finishing. And so what we did actually, we have combined these two processes, abrasive flow finishing and magnetorheological finishing. And after that, actually, we developed this process, magnetorheological average for finishing process. So this is the setup here. You can see this is the coil, magnet coil, and this is the core material here. And this is the cylindrical workpiece. You can say cylindrical workpiece. This is the two cylinder, top MRPF cylinder, bottom MRPF cylinder here. So this zone is exaggerated here. And there is a DC power supply is here. Through this DC power supply, magnetic field is applied, and by applying magnetic field, you can change the strength of this MR fluid here. So with the higher magnetic field, more strength to the CIP chain will be there. Okay, so this is the hydraulic unit. You can give up to 100 bar of pressure. This is the hydraulic cylinder. Two hydraulic cylinders are there. So one piston will be there here in the hydraulic cylinder, and another piston is there in the polishing fluid cylinder. And these two cylinders actually connected by a connecting rod. Here also these two cylinders are connected by a connecting rod. And there is a so limit switch is there. Through this limit switch, and there is a direction control valve in the pump. So this kind of reciprocating motion is given. So we can continue this finishing for a longer cycle. Okay, so for a longer time, and we can automate the process. Okay, so here actually through this hydraulic unit we can change the pressure, and through this magnet we can change the magnetic field, and by changing the current to the electromagnet we can change the magnetic field. Okay, so this is the process here. This is the experimental setup. We have developed similar kind of setup in our lab here. So this is the finishing zone. You can see there is just internal slots where we keep this kind of workpiece, stainless steel, silicon carbide, or any kind of ceramic material. You can put it here, or depending on your whatever this knee joint I have shown. So any kind of complex shaped workpiece can be polished by this process. Only thing is that actually this finishing zone you have to design, and you have to restrict the movement of this flow through the surface of the workpiece. Okay, so that is the thing we have to do. Okay, so this is the electromagnet which we have designed for giving the magnetic field there. So this is the fluid, how we have developed this fluid. So this is the continuous phase is the base material. What I told, actually it may be deionized water, it may be actually this oil-based media, and you can so after that, after mixing this one, actually we have to add this magnetic particles, and certain kind of additives and surfactants are added. Because these magnetic particles, it has a density is more than this base media, so there may be some certain sedimentation problem is there. So to reduce this sedimentation problem, we have used actually this silicon. Epithet grease we have used. So it is a thickening agent. So due to this epithet grease, actually these magnetic particle, they cannot actually, the sedimentation problem is reduced. And a small amount of actually the surfactants is used, like oleic acid. So what it does, this oleic acid, the surfactant, they make a small layer over the surface of these magnetic particles. So due to this small layer, actually it is generated, these magnetic particles, they not come close together. So that's why this agglomeration problem means when you are applying magnetic field. So what happens, actually all these ferromagnetic particles, which we are telling that CIP particles, carbon ion particles, these ferromagnetic particles, they come close together and they make a agglomerated content. So bigger size actually particles is generated, which is not required. We need actually homogeneous iron particles and homogeneous, and abrasive particles are homogeneously distributed. So this is the MR fluid, and then when we are adding abrasive particles into that, so it becomes as a means magnetorheological polishing fluid. So this polishing fluid without actually magnetic field, you can see this kind of thick fluid is actually generated, and then when we apply actually magnetic field, then it becomes very stiff. Okay, so you can see here actually under microscope, these iron particles and CIP particles are homogeneously distributed. When you are applying magnetic field, you can see this kind of chains are actually generated along the magnetic lines of force. So here magnetic field is applied in this direction. Okay, so here one thing actually I want to show here, I told that actually these CIP particles these are actually the special type of particles. So here you can see hysteresis low. Here this CFP, these carbon ion particles, here you can see this remnant magnetization is very less. Okay, so this because of this very less remnant magnetization, so this agglomeration problem it is very much reduced when you remove this magnetic field. Then what happens actually immediately these iron particles or ferromagnetic particles demagnetized immediately. Okay, so like that actually we have developed our polishing fluid. So after that actually we need the rheological characterization of this polishing media. So for rheological characterization, as I told, actually this MR fluid is a non-Newtonian fluid under magnetic field. Okay, so so what happens actually if we apply magnetic field here? So this at the center actually these abrasive particles are there, and these iron particles, it is these iron particle chains are there. Abrasive particles are being held. So along the direction of this magnetic field, and without magnetic field, this CIP and iron particles are abrasive particles are. So this white color it is CIP, and this black color these are abrasive particles. So it is randomly distributed. Now, if we apply certain amount of actually shear, what happens actually this chain structure means it bends actually. Then after with a high shear rate, actually this chains CIP chains actually breaks, and it gets less time actually to recombine. Okay, so what we did actually, we did actually rheological study. So rheological study, this means actually, so this non-Newtonian fluid under magnetic field, what happens actually, there is a certain amount of yield stress is there. So because of this chain structure, you have to break to flow the fluid. So without breaking this chain structure, you cannot flow. So means actually there is a certain pressure gradient you have to apply. Certain pressure gradient you have to apply. So when applied shear stress is greater than yield stress of this fluid, then only actually this fluid flows. So when started flowing, then there is a plastic viscosity actually is there. So this is the this graph is actually for Bingham plastic. So this MR fluid mostly actually it is represented by Bingham plastic fluid. Otherwise, Herschel-Barclay Casson fluid models also they consider. So in this case, actually, we have to know what is the yield stress and viscosity of this fluid. So to automate the process, actually, whatever this fluid we have developed, so it is required to get the yield stress and viscosity of this fluid. So in this direction, actually, magnetic field is applied, chains are applied. So in this direction, we are flowing this fluid. So this that's why actually we have developed a capillary rheometer, magnetoreometer, for getting this yield stress and viscosity. So this is the equation. So it is flowing through a capillary. So with a diameter of this 2r and length of L, and shear stress at the wall is actually del PR by 2L. And for Bingham plastic fluid, this is the equation. So if we know this actual volumetric flow rate and all these things actually it is known. So SW can be calculated from here. And from there actually, so this is the plot here, 4Q by pi R cube by shear stress here. So at different pressure, actually we have to plot this volumetric flow rate. So and then this line can be generated, and where this line actually touches, from there actually we can it is divided by this 4 by 3, and then we can get the shear stress of this fluid. And 1 by slope, actually it is the plastic viscosity here. So for that actually this kind of compressed air we have used, this kind of compressed air, and we have allowed to flow this actually this MR fluid through this capillary, and that is L by D ratio. L is the length of this capillary where we are applying magnetic field, and D is the diameter of this capillary. And from when steady state is actually achieved, we have accumulated whatever this MR fluid is there for a certain amount of time. From there actually we have measured actually this volumetric flow rate Q dot. And after that actually what happens in the same setup, MRFF setup only, actually this is the hydraulic piston, this is the MR fluid piston, this is the hydraulic piston. So we set certain amount of pressure from this hydraulic unit, and we have allowed to flow this media through this and through the actually this capillary here. Okay, so like that actually we have measured this yield stress and viscosity of this fluid. And after that we got one rheometer. So this is Anton Park NCR 301 rheometer. Here this parallel plate rheometer. And here actually there is an option of Magnetorheological device. So they are the only company who developed actually this kind of MRT device, where actually you can apply magnetic field also, because our fluid, it is a non-Newtonian fluid under magnetic field. So there is a tool master here. So this tool master, it is attached here. So this tool master, it rotates with a certain RPM. At that time, magnetic field is applied. And this is the bottom plate here. On this bottom plate, we put certain amount of MR fluid. So this is the 20 millimeter diameter, and this the gap is actually 1 millimeter. When it tries to rotate, and then there is a resting torque is generated. So this resting torque is proportional to the shear stress, and whatever this shear rate is calculated from this rotational speed of this tool master. And if you plot all these things, you will get this kind of points, and all these points actually fitted with a different model, actually Bingham plastic, Herschel Berkeley, and custom fluid model. And then from this R-square value fitting parameter, actually we know that which model actually better fitted. So certain experimental things actually we have done without magnetic field. We have seen that actually these abrasive particles, because there is no bonding strain, so these abrasive particle will flow over the surface peaks, and it will rotate, and then it will move like that. And when we are applying magnetic field, this kind of bonding strength will be generated, and this abrasive particle will be held by these CIP chains, and these surface peaks will be removed from there itself. Okay, so so these CIP particles, they don't take part into the metal humal, only the abrasive particles take part into the metal humal. Okay, so there are certain things are there actually. This in MR fluid, you can see here, it is not a parabolic profile. So here actually in MR fluid, there are two zones are there. So this at the center, this is the plug flow region or solid core region here. So there is a certain radius, I can say this is the critical radius. Up to this critical radius, actually this shear rate, rate of change of shear actually it is 0. So, but here there is a, here in this zone actually this fluid is flowing. Because actually shear stress is maximum at the wall, and it is minimum or 0 at the center. So actually this fluid is actually here in this zone, fluid is actually sheared here. So it is actually yielded zone, it is actually unyielded zone or plug flow region. Why I am telling this one, actually we need actually this plug flow region as much as possible, because in that plug flow region, this abrasive part of this bonding, these chain structures are not broken. But if we have actually have more shear region or yielded region, so in that case actually there is a chances of rotation of these abrasive particles. Okay, so we have to make sufficient amount of magnetic field. We have to apply sufficient amount of magnetic field so that maximum portion of the fluid actually it should be in the plug flow region. Only that at the wall, certain amount of yielded zone will be there. So with this actually you can see this the shear stress versus shear rate plot here. So we have found that actually this is actually shear thinning fluid here. So here you can see this viscosity, it is reduces with increasing shear rate. So that reason actually already I told earlier why to show actually. So this is our finishing zone. Like this is our finishing zone here. You can see this is the finishing zone. I can so this is the finishing zone. In this zone only we are applying magnetic field. So for simulation purpose, what we have done, we have used actually axisymmetric thing. So this kind of axisymmetric we have used. And also actually up to this point actually we have solved. Up to this point we have solved. So from here to here, this is actually one zone, and this zone actually told this the zone 2, and this zone actually we have considered this one is the zone 1. So this is the zone 1 where we are not applying any magnetic field, and this is the zone 2 where we are applying magnetic field. So after that, actually some modification we have done. We have rotated this fluid here. We can see, you can see here this chain structure, amorphous chain structure, how it is rotating inside this actually cylinder. So this real time actually we have taken this picture, and as well as we have taken video also here. And this fluid you can see with this kind of south north this configuration, and this north south this configuration. You can see this kind of the internal surface of this fluid means this fixture, this chain structure, how it is forming here. Okay, so few experimental results. So you can see this here actually this magnetic field is rotated so that this fluid can be rotated inside. MR fluid can be rotated inside this finishing zone. Okay, so that entire surface can be polished. So this is the workpiece fixture here at the internal surface. We kept this kind of workpiece here. This is experimental setup we have developed in our lab. And now certain forces actually we have to understand. So when it is flowing through a cylinder here, so these abrasive particles which are actually touching to the workpiece surface, these are called actually active abrasive particles. So these active abrasive particles, what are the forces are there? So this fluid is through this cylinder, there is a pressure gradient. We have applied certain pressure gradient here. So because of that, actually one radial force will be there. So this radial force and one axial force will be there. So this axial force, this radial force, and also these magnets are actually north and southward is kept here. So magnetic force also will act in this direction. So on the abrasive particle, this radial force is there, and then this magnetic force is there. And then when these are called actually indentation force, and this indentation force helps in actually indenting the abrasive particle into the workpiece surface. Although this indentation is very less, it is in the nanometer range. This indentation, after it is indented into the workpiece surface, if you move that abrasive particles because of this axial force here, because of this axial force. So because of that, actually this whatever this indented portion is removed, that much material is removed from the workpiece. Okay, so this radial force, magnetic force, these are the indentation force, and axial force, it helps in removing the surface undulation, and these two forces helps in indenting into the workpiece surface. So from simulation, actually simulation study, what we have done, actually this axial force and radial force, basically this radial stress and axial stress, shear stress, we have calculated from this CFD simulation, and from maximum simulation, actually we have calculated this magnetic force, how much force is there on this magnetic force we have calculated from this maximum simulation. And when this fluid is rotated, then the centrifugal force also act as an indentation force, and there is a coriolis force is there that we are not going to show this simulation, only this MRFF, this simulation we are going to show. And when this fluid is rotating, then this abrasive particle will come in this kind of helical path. So because of this helical path, actually more area on the workpiece surface can be polished. So some flat workpieces we have polished. Actually this you can see it is a final polished surface here on the brass workpiece. This kind of process patterns are generated. So because actually we are giving reciprocating motion as well as rotating motion over there. So this is the FM picture, and these are the flat workpiece. You can see these are the highly reflecting surfaces are there. Surface profile before finishing, after finishing. So you can see here up to 50 nanometer. We have achieved up to 50 nanometer here. So this is the bearing area curve, initial area curve, and is the final area curve. So bearing area curve where friction is there, so it is very much important. After that, we have done experiment on cylindrical workpiece. Before finishing this kind of workpiece, you can see it is made by actually boring operation. So after finishing, you can see this kind of mirror finish surface, where you can see it is reflected here. So up to 16 nanometer we have achieved on. These are the stainless steel workpiece. So achieving this kind of 16 nanometer, it is very much difficult by other process. Okay, so also we got this kind of process pattern there. Okay, so outer roundness also very much important. Although it looks in naked eye, it is a circular profile, but you can see this kind of non-linearity is there. So maximum circumscribe and inscribe circle, what is the distance? That is called actually outer roundness. So this outer roundness from 5.17 to 3.39 we have achieved. Okay, so now we have done actually experiment on this prosthetic implant, that knee implant, whatever I told. So for that, actually, this kind of tool we have developed here. Permanent magnet we have used. So this is rear of permanent magnet, NDFB N52. Okay, so maximum simulation we have done. Here we know, and here this kind of mu metal we have used. This mu metal helps in actually concentrating whatever is magnetic field into this area. It will not allow actually to magnetic field to go outside. So, so it is concentrated, whatever this magnetic field is concentrated into this area, and this kind of magnetic field contour plot you can see here. This kind of spherical shape is generated. So with this, actually, this main intention is that actually to get this kind of point contact basically. So with this tool, and it is attached to a milling machine basically. So it is attached to a milling machine head, and at the bottom of this milling machine you can see this kind of this is the MR fluid which is used, and just we want to show actually this this is the tool here, and this is the finishing spot here. You can see this is the finishing spot you can see here. Okay, so after that, just I'm coming to this how this actually finishing happens. So this is before finishing, and this is the after finishing here. You can see the component, how this workpiece is hold. You can see this is the knee joint, this femoral component, femoral part of this knee joint. So there is a 4-axis. It is rotated with a 1 or 2 RPM. It is rotated, and it there is a shaft is here. So it is like actually in lathe machine, you know, this chuck. With this chuck, actually this chuck, this shaft is actually held, and this right hand portion it is kept on this rest here. Now it can rotate about this axis. It can rotate, and now this tool and this workpiece actually there is a XYZ 3 motions, and this rotation also there is a fourth axis actually is there. So it is a 4-axis CNC machine. So by this process, actually, this entire surface of the workpiece can be polished. So you can see in one go, actually, this entire surface of the workpiece can be polished. So this is the finishing spot here. Means finishing spot. This whatever the surface particles are here, which is kept just at the bottom. So it takes actually around 30 millimeter. So every time actually this tool is perpendicular to the workpiece surface. So it is perpendicular to this workpiece surface. Now it is rotated with a very small RPM. And we can see this is the different zones we have divided to measure that how it is polishing. So you can see this is a freeform surface. There are so many planes are actually involved here. So it is very difficult by actually manual polishing. So it is very difficult, and we need actually uniform polishing everywhere. So that's why actually we have made in such a way that every time this tool is perpendicular to the workpiece surface. Okay, so here it is the extreme right portion, this is the extreme left portion here. And we have found that actually this entire zone, this final surface, the standard deviation is 19.23. And that is a huge improvement in the workpiece surface. So you can see final one, actually this is in the nanometer range. It is the lowest one, it is 20 micron, 20, sorry, nanometer. This is actually at different zones, at 5 different zones. We have considered this average one. This is the final surface finish, and this is actually made of very hard material here. It is the titanium alloy, so Ti6L4V, so of grade 5. So this titanium alloy of grade 5, it is used for making this kind of prosthetic implants. Otherwise, cobalt chromium alloy is also used. So we have used actually this titanium alloy. Now, actually, this some gears also actually we have polished. We have done simulation also for this gear, but we are not showing here. So this kind of small gears actually we have polished here. You can see this is the fixture actually where we flow this media through this gear. These are the holes you can see through this hole. we are flowing this media, and this is the magnet fixture here. Okay, through this magnet fixture, we are applying actual magnetic field, and also at the same time it is rotated. Okay, so how this fluid is flowing through this? We have simulated this one also actually using COMSOL. We have simulated how this fluid is flowing through this gear. Okay, so you can see different surface of this gear actually have whatever these bars are there, all these bars, everything is removed actually. Whatever this initially these bars are there, these bars are actually removed here, small bars, these bars are removed. Okay, so now I'm going to start actually this whatever the simulation work we have done. Here actually we have considered only this MRFA process without any rotation. We have not considered any rotation. So this is the finishing zone already I told. So this zone we have considered as this zone 1, and this zone we have considered as this zone 2. And here this in zone 1, whatever this initial this velocity, actually this average velocity, we have actually measured this average velocity from the piston movement and from the volumetric flow rate, how this flow is flowing. From there actually this average velocity we have calculated, and then actually this initial average velocity, uniform average velocity we have considered, we have given this one, and then output actually it is calculated from here. Okay, so in this zone, this is one zone we have considered, and this is the finishing zone. We have this one actually we have considered as the finishing zone, and in input to the actually finishing zone, we have whatever this output in the zone 1 we have considered as the input for this finishing zone here. Now we can see so there are different simulation. So CFD simulation we have used for getting this axial force and radial force, and magnetic field simulation we have used for getting this magnetic force. And from this actual simulation model, we have done surface hardness analysis. Okay, so these different zones already I have told. So this is the continuity equation, and this is the momentum equation we have used. And as I already told, actually this medium we have considered as isotropic. Although this media actually consists of actually these abrasive particles, iron particles, solid particles are there. So entire media we have considered as a fluid actually, and its viscosity actually we have measured at a different concentration of CIP particles, at different concentration of these abrasive particles, at a different concentration of this base media. Its viscosity and yield stress already we have measured earlier using this Anton-Bar parallel plate geometer. Okay, so this viscosity actually it is already known to us at for a different actually concentration and of these abrasive particles and CIP particles and base media. So that's why actually here we have considered this media as isotropic and homogeneous media, and we have considered this one as an incompressible fluid, a steady flow condition we have considered. And as the fixture is cylindrical, we have considered as a axisymmetric case, and that's why actually this in RZ plane we have solved this one, and that is the swirling motion actually we have not considered here. So we have solved 2D axisymmetric problem. So as I told, actually there are two zones actually there. In zone 1 actually where we are not applying any magnetic field. So in this zone actually this uniform velocity I told from this piston velocity. From there actually we have measured, and after that we have calculated this uniform velocity here. So at the wall actually this no slip condition we have considered, and here at the axis axisymmetric condition, and here at this output actually we have considered this del V del Z actually is 0. So here also we have considered actually the in zone 2 actually what we have considered whatever this radial velocity and axial velocity whatever we have got from here we have used as an input to this as an input to this actually zone 2. So wall no slip, and here axisymmetric boundary condition, and then here output actually we have considered again del Z equal to 0. So fully developed condition we have considered. So at this zone also, so in this zone actually we are viscosity of this this fluid actually it behaves like a Newtonian fluid, non-Newtonian fluid, because we are applying we have applied magnetic field here. So these are the actual boundary conditions. So we have discretized in Gambit. We have discretized different discretization scheme we have used. So M1, M2, M3, 3 different discretization schemes. So this 200 actually along this axis we have considered this 200. Okay, so quadrilateral element we have considered. And zone 2 also you can see in this small area, because we are applying magnetic field here also we have along this we have considered actually 200. This divide in 200 points, and according to the dimension other points, other areas are actually discretized. Okay, so here now we can see now viscosity model here. It is very much important because we have considered here actually Bingham plastic viscosity model. So there are 2 zones are there actually. So if you consider this one as the Bingham plastic one here, so at 0 shear rate you can see here actually yield stress is tau y, when then actually when applied shear stress is greater than tau y, in that case actually fluid shear here. So after that actually this cannot be solved because actually shear rate here is 0, so there will be discontinuity here. So that's why actually people use bi-viscosity model here. So AC and then CD. So here high viscosity they consider, and after that there is a plastic viscosity it is known. So this mu0, that is a high viscosity, it is 1000 or 2000 times of this plastic viscosity people consider. That is a critical shear rate. So before that actually this high viscosity, after that this plastic viscosity they consider. So this is the modified bi-viscosity model, when shear rate less than actually critical shear rate, then mu equal to mu0. When shear rate is greater than actually this critical shear rate, in that case then mu equal to plastic viscosity plus tau y yield stress by shear rate. So after that actually this here this one also there is a discontinuity at gamma dot c, critical shear rate. So after that actually this Papa Nastasu, so what he did actually, there is a combined equation he has considered. Shear stress is equal to tau y 1 minus actually e to the power minus m gamma dot plus mu p into gamma dot. So here shear rate actually it is a function of means viscosity is a function of actually shear rate. It is a function of actually magnetic field also. So so this is the viscosity. It depends on actually shear rate. So this one single equation can be utilized actually for both the zones, for solid core region as well as for this shielded zone also. For 2 zones actually it is used. So you can see here actually with higher value of this n, and then with very high value of this n here. So in this case it is same with the very high value of n, it actually mimics with the actually this Bingham plastic model. Okay, so so this m is actually, it is called stress growth exponent here. Okay, so these things actually work for actually MUA divided by d. D is the diameter of this whatever this cylinder we are considering, and this is the stress growth exponent. So this is the velocity here. So it so this equation valid for this condition only. So numerical method actually what we did for convective term and this viscous term actually for discretization we have used second order upwind, and we have used actually this simple method we have used for pressure and this velocity coupling. This simple method we have used. Okay, and so this viscosity actually every time it is updated. So what we did actually, we have used Fluent 6.3 we have used, and Gambit we have used for discretization, and in Fluent we have used actually this user defined function. In that user defined function every time this viscosity is updated. Okay, so one user defined function we have used, and after that actually we have used a grid independent test, and we have found that actually this maximum velocity for zone 1 and zone 2 when it is less than actually 1%, then from that actually we have find out which grid is suitable. For zone 2 also we have done similar thing, okay, for a different grids. And you can see here actually there are 2 zones, so it is axisymmetric. Here this axis of the cylinder here up to this one actually the solid core, and after that actually this is the yielded zone. It is actually done at for 0.5 Tesla magnetic field. So here property what magnetic property what we have given here, this fluid property what we have given, fluid viscosity and yield states, we have given actually from rheological experiment we have done. From there actually one equation we have, empirical equation we have developed at what concentration, what magnetic field, what should be the yield stress and viscosity. From there, from that input actually we have given this yield stress and viscosity things. Okay, so after that actually this it is validated with this with analytical equation with a different Bingham number, and Reynolds number we have considered this one is a Reynolds number. And then Chabra and Richardson they have this developed this analytical equation, okay, for this yielded zone as well as for the solid core region also. From there itself actually so this continuous line, it is actually analytical equation on other things. Actually these are the points here which is actually simulated from our console simulation, so for a different Bingham number. Okay, so from there actually we found it is working. And after that actually this is the contour plot for zone 1 where we are not applying magnetic field. What we have found that actually although in the zone 1 where we are not applying magnetic field, but certain amount of actually yield stress we have found on this fluid, and viscosity also, this plastic viscosity we have found. So we can see here actually this the extrusion process in that zone from MRPF cylinder to actually this workpiece cylinder here, workpiece whatever is cylinder here. So this is the contour plot and this is the vector plot here, and whatever this output here we got from here, we have given input to the for this finishing zone. So this zone is important for us. So this is the contour plot here. We have seen that actually up to 0.01 meter or 10 millimeter, so it got actually fully developed actually. So after that, so this is the one, and this is the solid core region, this portion, and this is the yielded zone here. So this is the vector plot, and we have seen actually certain kind of actually in this direction, this velocity profile in this direction, certain it is inclined little bit. Okay, so it helps in actually to scooping up these surface undulations from the workpiece surface in the finishing zone. And without magnetic field, so you can see this kind of parabolic profile is there. Okay, so after that actually up to this one, this is our actually CFD simulation. After that we have done actually magnetic field simulation. So this is the equation actually, this magnetic force can be calculated. So this is the mass of this individual CFD particles, susceptibility, this is the gradient of this magnetic field, this is the magnetic field at a different points. So this is the image curve for this MR fluid, whatever this MR fluid. So there is a vibrating sample magnetometer VSM is there. From there itself actually you can get the image curve. Okay, so at different magnetic field, applied magnetic field, you can get the what is the magnetization is there. Then you can put it over there itself. Actually, from there you can calculate what is the magnetic force on individual abrasive particles. So, so this is the contour plot, magnetic field contour plot. So north pole and south pole. This is the workpiece fixture. It is filled with MR fluid, and with the experimental results, actually it is validated. We can see here. And then this chain structure you can see where it is randomly distributed, and then this chain structure you can see CIP chain structure here. And then we have modeled actually these CIP particles and abrasive particles. So these abrasive particles, it is touching to the workpiece surface, and after that actually we have used actually this kind of BCC structure, body center cubic, and at the center actually these abrasive particles are there. It is surrounded by this kind of abrasive particles. From there actually how much forces are coming. So we have calculated this radial force, shear stress, radial stress, and shear stress we have calculated. So from there itself actually we got the value how much forces will be coming on this abrasive particles through this CIP chains actually. So these are the total magnetic force. So this magnetic force as well as this radial force will give the what is the indentation for maximum indentation. So this is the abrasive particle, one half we have shown. So this is the indentation force. It is combination of this magnetic force and radial force, and that is the axial force. It is calculated from the shear stress, and then this radial force is calculated from the normal stress or radial stress. From there, it is indented. This much is indented. So if this force is known, actually how much indentation is there. From there, how much means after it is indented, it is moving there. This much volume of material is removed, and we have. So we have seen that actually this shear force should be more than the strength of this material. So it is found, and this shear force should be more than the strength of this material. So we have found it is more than that. Resistance more than resistance. So from there we can see that actually this abrasive particle really indenting into the working surface. And it is actually this of the abrasive particles. So whatever the surface peaks, it is removed by this abrasive particles. So some kind of modeling we have done. Okay, so after that actually we have done a parametric study for a different CIP particles concentration. Okay, so these are the inlet axial. So it is for zone 1 basically, and this is for actually for zone 2, and this is the shear stress and this is the radial stress plot. Okay, for zone 2. Effect of CIP concentration also we have done like that, and then we have done actually this surface finish modeling. Okay, so this one actually surface final surface finish which we have actually from surface finish modeling we got, and this is actually this experimentally measured one, and from there by experimentally we got actually 0.09 micron, and from simulation we got actually this 0.07 micron. So this surface finish modeling, so this input is actually this whatever these forces are there, and that forces actually we have calculated from that whatever the stresses are there from CFD simulation and from magnetic field simulation, and from extrusion pressure also we have done. Similarly we have done. Okay, so so for different pressure, so this is actually for different pressure. So you can see inlet means initial surface finish. This is the final experimental, final simulation one for finishing cycle also. So these are we have done. So for it is related to that manufacturing. So here actually what we are doing in our lab. So this is the finishing setup. Already I have discussed this one. So this is another MRF setup we have developed in our lab. So this is another setup we have developed. This 3 MRF setup we have developed in our lab. Other than that, actually we are doing plasma polishing. We have developed here for polishing this kind of actually HRG cell and this kind of actually prism, which is made of quartz. Okay, so these are actually in collaboration with ISR. We have developed this plasma polishing setup in our lab. And other than that, actually this micro ECM, you can see small micro channel we can develop. So this is this tool actually its diameter is around 70 micron here. So we have reduced actually more than that also, around 20 to 25 also we have reduced here. So this is the micro ECM setup. Any kind of micro channel, micro hole, micro things actually we can micro milling also we can do using this setup. And now we are doing actually this micro EDM also. So thank you for listening. So I'm stopping here, because up to 11:30 I've been given time. So if you have any questions related to this one, actually you can ask me. Thank you. Thank you all for listening, for your presence.
Any questions, please? Any questions, please?
Although it is little bit means
Yeah.
I'm from manufacturing background, so obviously some practical thing actually we are doing, experimental thing we are doing more, and for supporting our this experimental work, work. Actually, we are doing some simulation work also.
No, it's a brilliant idea actually, and I hope that it fills the one part of the spectrum, whole spectrum of the areas which CFD can cover. So it was a really nice talk. So thank you, Dr. Das, for your valuable time and talk. Now, may I request Professor Murali Damodaran to present with his talk?
Okay, thank you.
Welcome, most welcome, Das.
Hello, Murali here. Are you guys
Yeah.
ready? Maybe start in 5 minutes because the talk just ended. Let them warm up a little bit. Is it okay?
Yeah, fine.
5 minutes time.
Sure.
I will just share something. No problem.
Yeah. Meanwhile, you can
Yeah.
do that.
Are you able to see?
Yeah. Can you make it full screen, sir?
Yes. How about
Yeah.
now?
This is great. Yeah. Wonderful.
Okay. Just want to move this somewhere else.
Yeah. Full screen is visible.
Okay, so I will start in maybe just give me maybe 3 to 4 minutes. I will start. Just is that
Yeah.
okay with you guys? I don't know if you want me to start now. I can start, but I thought that previous lecture just ended.
It's fine, I guess. We can
Okay,
start.
sorry, because I guess you guys have to go for lunch. Okay.
Yeah.
All right. So today, lecture, I think from now till uh, the end of the day, we will be talking about certain concepts which are useful from the point of view of machine learning. All right. So this is something which youngsters who are looking for new jobs will have to contend with. And for that, you have, before the machine learning craze came into being sometime around 2012, uh, in the late 80s and early 90s, engineers were already looking at what he called the reduced order models for flow prediction. So this lecture will be to introduce this concept to you so that you can consider using some of this for your own work. The scope of the presentation will be as follows. I will be talking about what is called the model order reduction and a little bit of history to put the topic into context. Over the last 20 years, there have been a lot of developments in this field, and so grouped together to call the model order reduction. And the technique is used in many areas, not only engineering, but in computer graphics, in genetics, you name it, it's all there. And because the topic is so wide, I'm not going to talk everything that is under the sun, but I'm only going to focus on proper orthogonal decomposition, which go by the name of POD. Basically, because this is widely used in fluid mechanics. And since our topic and theme is all about fluid dynamics, I believe this will be the useful topic to start. And I will also talk a little bit about some variants of POD and their relation to singular value decomposition, which is called SVD. These are all concepts from linear algebra. Okay, so if I look at flow modeling, like in my previous lecture, we were talking about high-speed flows, finite volume methods for calculating the Navier-Stokes equation. So if you look at that, you will see here, this is the highest fidelity model. Okay, the next level will be the Euler equation. For certain types of flows, I can neglect viscosity, and so you have the Euler equations, which is still as complex as Navier-Stokes, except that I don't have to worry about turbulence modeling or viscous effects. And by making the irrotationality assumption, I can neglect vorticity and entropy production, and you get what is called the full potential equation, which is just uh, solving one variable. And you can further linearize this linearized potential equation, and also for small disturbances, you have the transonic small disturbance. So if you look at model fluid dynamics models, increasing complexity of the model is like this. Here, I only need to solve one variable. Here, I have four. Three velocity, one density and energy, and here also I have five variables. And for Navier-Stokes, I need to worry about turbulence modeling. So early attempts, they use what is called the thin layer Rand's equation, which is something akin to the boundary layer model. And then you have the Rand's model, which has stood the test of time for many, many years. And then you have LES and DNS. So this is increasing complexity at the high fidelity level. Okay, so this is the picture which I have taken from Bendixson and adapted it to. So if you look at the computational simulation based on high fidelity mathematical models, that attempt suffer from increased complexity, increased dimensions, and both increases with geometric complexity. Like for example, if I have an airfoil, it's a 2D geometry. The mesh is a planar mesh. If I have a wing, it is 3D. If I have wing with flaps, I have more stuff to handle because I have moving mesh and full aircraft. Okay, so this is really top of the game, and you need heavy computer resources, because if you go and do this, Navier-Stokes, say LES or whatever, for this kind of things, it's going to require a lot of computational time and storage. Okay, so if you look at back at the slides where I did the 3D finite volume discretization of the Navier-Stokes equation, when you do that, you will essentially get coupled first order ODEs, okay, where W is the unknown which you want to solve. Finite volume gives you this, and this Ri will contain all the convective terms, the viscous terms, the discrete forms, artificial dissipation, everything there. Okay, so if I want to solve this, let's say if I solve it on a mesh of 10 to the power of 9 cells, then I'm talking about the solution of 10 to the power of 10 ODEs at every time step or iteration. So that's going to be a very large computational effort. Of course, the task has been simplified by developments in computer architecture, like parallel computing, multi-core, and GPUs. Okay, so people can still do this, but you have to understand that not many people have access to, like exascale computers, which is what people are using. In the US and various other places. Okay, exascale is the future, and so let's see what is happening. So in view of this, as engineers, you want to have a certain degree of high fidelity in your predictions, instead of using low order flow models and getting away with it, which is okay. So we talk about model order reduction. So what it aims to do is, question is, can we construct a low dimensional model which can capture the dominant behavior of the high dimensional model? So it's like this one here, this cartoon, this is the Stanford bunny, which you find in many computer graphics papers. So I have a very fine mesh triangulation used to represent this rabbit. Okay, this is the next level of coarser, and this is the coarsest mesh. But if you look at this, so this is a high dimensional representation of the rabbit, and this is the low dimensional. Okay, so this is, but here, this one is very easy to generate. It does not capture everything that is there in the high dimensional bunny or rabbit, but roughly you know what it is. So that is the basic concept behind model order reduction. So the resulting model order, the reduced model, will not be an accurate version of the high dimensional model. Okay, but it is one which has a minimum loss of the fidelity of the high dimensional model. Okay, so it can be looked at, okay, as a simplified high fidelity model, giving you enough richness for your work. Okay, so that is the whole concept. How do you do it in, say, fluid mechanics? Okay, so if you look at the early examples of model order reduction, if you look at 1807, you have the Fourier series. The Fourier series representation of a function, where you represent a function by sums of sines and cosine, that is a very early form of a MOR. And then the work of Lanchos and Arnoldi, okay, in matrix reduction, size of reducing the matrix to tridiagonal and smaller matrices, because when you are solving, say, systems of algebraic equations and all that, you need to, if you have a large system, you end up having large matrices. And so there were some efforts by various mathematicians to see whether they can come up with a quick way to solve the equation with a smaller size matrix, or even do tridiagonal. So the MOR, if you look at the history, right, it is actually, the term actually started the development in the systems and control theory area. You find that there are a lot of interesting methods in control theory. It is one of fascinating fields, which one can get into. The fundamental ideas of MOR actually appeared during the 80s and 90s. Okay, and it has been a very active area of research in many fields. And over the years, there are a number of techniques that fall in this overall thing called model order reduction. So I'm listing some of them. We are not going to cover all of this. That may be done in the future if we develop new dedicated courses in the era of machine learning. But basically, you have parameterized PDEs, projection-based model order reduction, PODs, linear dynamical system, balanced truncation, whatever. Okay, so we are not going to talk about. I'm only going to talk about the POD. Okay, in this lecture, because we have only limited time, and we would like to. So the POD is actually called, the proper orthogonal decomposition was widely used in fluid mechanics and meteorology. And this was first made aware to the research community in 1965-67 by the famous Professor Lumley, the late Professor Lumley, in 1967, via this paper. But if you read an article which appeared in Resonance by Professor Rodham Narasimha, who recently passed away, Resonance June 2011, the article is actually Kosambi and POD. Kosambi is actually a very famous Indian mathematician. I do not know many of us really know a lot about him, but he's an interesting person if you read about him. And he was the first one to actually show the concept of POD, and it was published in 1943, okay, in this journal. And there were others who developed a similar concept independently, Karhunen, 1946, Pogoshev, Obukov, and various others. Okay, so POD goes by many names in various fields. In statistics, it is called principal component analysis, PCA, which you see a lot in machine learning and so on. In mathematics, it goes by Karunen-Loewe method. Okay, so these were some of the early developers of this technique. Okay, so I would like to, how I'm going to conduct this present this material today is, this is quite a difficult subject to present. And if I look at it, there are many books on POD and MOR, and most of the time it is written in a manner that is very difficult to really understand or difficult for engineers to appreciate because you need a certain level of mathematics. And there are a number of tutorials that have been written. Okay, and I think one of the first tutorials I read was actually written by a person who just graduated from a PhD from US and is now currently a professor in IIT Kanpur. And that was the first tutorial, but the example used was mechanical systems. All right. So there are many, but I'm lucky enough to come across this tutorial. So I'm acknowledging that I will be using this recent tutorial written by Professor Julian Weiss of TU Berlin, Germany. He wrote a tutorial on POD directed as engineers. Okay, so that appeared as this paper in the 2019 AIAA Aviation Forum in the US. So the paper is available here. You can take a look. And he has actually made that paper available to this link. Okay, he's a head of the aerospace department in TU Berlin in Germany. And the examples which he has used in this tutorial is also provided in a link. Data for the MATLAB code. Segments of the MATLAB code are in this paper. So the reason for using this is to have some of you go at this tutorial with the data and learn the things by yourself. And so that was my prime motivation for using this tutorial as a base. So everything you see from here on outwards is actually taken from this paper. Okay, so this is a test problem. Let's say there is an experiment. I can do an experiment and CFD. So this is a flow which is coming in. There is a depression here. So that when the flow comes here, it will go like this, and so there will be a separation bubble somewhere in this dotted box. So you can actually create an experimental apparatus in Perspex and then use your PIV, which is a very interesting experimental method, and obtain the velocity field at the random points inside this box. So this is a PIV box area, the test section of interest. Okay, so for when I do the measurement, I can do just shine your PIV laser into the various points, and collect the data sample. Now on the surface, you see the surface, this is a solid wall. I can actually put the sensors there to measure, say, pressure and so on. Okay, so I'm interested in this domain. So this is basically a domain. So experimental apparatus is a 3D stuff. So inside this domain, okay, the flow field is actually a 3D velocity field, which is given by this, and it will be a turbulent flow. Don't worry about this boundary layer bleed and all that. I'm not going to talk about that because it's not of concern to us. Our concern to us is this box here. So inside this box, there will be a total velocity field, okay, which is going to be turbulent. So I can actually, do like what Professor Dr. Madhukar was talking about in the turbulence modeling, where I can split it into the mean velocity components and the fluctuating velocity components. Okay, so each of these components I can do that. So if I'm looking at say a section like this, okay, so that is essentially 2D. Okay, if I have a 3D, say suppose this is extending in the Z direction, then I have many sections like this stacked in the Z direction. So I'm just taking 2D just to illustrate the concept. The PIV data set, which is provided by the Professor Weiss in his paper, consists of 3,580 vector fields in this domain here. So basically, if I have a grid, the grid will contain nx number of distribution in the x and y direction, and I will have 129 points along here and 45 points along there. So that will give me 5805 points. That will give me that many velocity vectors. Okay, the velocity vectors can be has components u and v, okay, measured in the and the data is sampled at 900. So if I, from the PIV data, if I plot, I can look at all these velocity components, but I'm only going to look at the longitudinal velocity component, that is the flow in the x direction only. Okay, so here this is actually x and y, but I'm only looking at the flow in the x direction, so u. All right, so if I plot the instantaneous longitudinal velocity field at that point, I will get a contour, contour plot, which looks very convex, almost like an art. Okay, can't make any sense out of it. So what you do is you decompose the velocity. You know the mean velocity. You can, and then this is the fluctuating component can be written, and you can actually do a time average mean velocity over there. And then you plot the contours of the time average longitudinal velocity only u, not uv, in that same thing, because everywhere there is a u component. So if you plot, the contours will look like this. And in this contour, I look at 2 points. Okay, so if you look at this field, it is a time-dependent field. So at every point, these are just 2 points, but there are so many other points in this domain, but I'm only looking at these 2 points. They're close to each other. They're also in the same region, okay? So if I look at A and B, there will be fluctuations, and the fluctuations will be a function of time, okay? And B also. So there will be 2 variations in this fluctuating component, which I can plot. Okay, the data from whatever data is measured over time, I can plot the fluctuation velocity components. This is the fluctuation velocity component in at point A, and this is at point B. Okay, so this is 2 random signals. I have 2 random points and random signals. Because they're close by, they may have some correlation. Okay, so you look at the data at these 2 points. The data is contained in arrays size m, okay, nt, of uati and ub. That is the the fluctuation velocity components. I'm going to put it in this ua and ub, and I'm going to assemble a snapshot matrix S, where the first column I'm going to put all the velocities which I measure with basically this time signal. Okay, what is the velocity of this fluctuation u? The blue is at A and the red is at B. So the first column basically contains that information, and the second column will contain the information of the point B. So that is the fluctuation velocity component. Okay, so now you have to construct a new snapshot matrix for the fluctuating velocity component at this point. This is the total thing. So that you break up the mean, you take it out. So I'm going to put my fluctuation velocity component metric, the same thing. This is the random velocity fluctuation, which is you see in this plot. This is the previous plot, which is this one here, okay, which you are not going to do. So that will be the snapshot matrix U containing the data, this blue and red data, okay. T starting from 1 going to M, that is 1 to M. Now, I'm not only constrained to represent the data like this, I can also plot data. I have two parameters here. One is UA and UB. So I can take, because I have two components, I can draw, plot this data at UA and UB, okay? So I take this fluctuation and plot it here. This plus sign basically show the same data, okay? I have all this data point, and that data appears like this, okay? This you can do with any computational platform like Python, MATLAB, whatever. You can just plot it. So I'm just plotting one of the fluctuation velocity component at A is in the X, in the, you can call it the X axis or the Y axis, but the axis is actually UA prime and this is UB prime. Okay. If you look at this data, it looks like most of the stuff is actually enclosed by an ellipse. Okay, I mean, you can see from the pattern. And there's some, so the shape of this patch is something like an ellipse. Okay, so what we do, this is a statistical term. We want to find the covariance matrix. This is very well defined in statistics and also in in whatever we do. So here is the definition of the covariance matrix, and we already have our data, which is this, which is already computed, our U matrix here. Okay, so we take that and carry on this operation, and you will get this, expand it out, you will get this. Okay, the diagonal terms are the variances of UA and UB, and off diagonal are the covariance. Okay, so they basically tell you how the data is correlated. Okay, so like if the off diagonal terms are non-zero, then this two data UA and UB are very well correlated. If U is diagonal, that is, if this is 0, then these two will be uncorrelated. It will be good to know how the data are related to each other. So if you take for the given PIV data set, if you go and calculate the covariance matrix, you will find that for the given data values, it will come to this. Okay. And the amount of correlation is given by this coefficient. Okay. So this also you can calculate, it comes out to this. It depends on this. And the total fluctuating kinetic energy of the data, okay, will be this one here. So you can see this term, these are the diagonal terms, okay, C11 and C2. Okay, that because it is the square of the fluctuating, that is something like the kinetic energy. And that is what is called the energy of the data set, because this is velocity, you can interpret it that way. Okay. So if you look at the way this data is plotted, I have UA and UB here, and these are plotted. The natural bases are the unit vectors 1 and 0, and 0 and 1. Okay. Now the question is, I want to put it. Can I, instead of just sticking to the natural basis, can I project it to other bases, like at the inclined line along this, this line here. Okay, so I will consider a basis vector. The unit vector will be this one here. Its components are that. And then I compute the dot product. So this is basically the projection of the fluctuation, the velocity fluctuations to that. So this you can calculate, and you will get this one here. And I think there's a mistake here. I will correct it. Okay, so U phi. Okay, if I do U phi, I multiply and I construct my A matrix. Okay, and that will be this one here. Okay, this is just a dot product of all. And the basis, if I choose this basis, okay, as this one here, 2 square root 5 and 1 square root 5. Okay, that will be this line here, this line here. And then I project, I calculate my variance. The variance, we already know what is the definition, and it turns out to be 7.19. And if you look at the variance along the natural basis, okay, that is 4.92. And the other one is 5.01, so it's less than this. So somewhere along this, you can find a line where the energy, so the variance will be large. Okay, so that's what. So question is, how do we find the basis vectors which will give the maximum variance? Okay, so this is what we want to do. So there are infinite basis vectors. And if you look at this particular set of data, we know that the maximum variance is along the major axis of the ellipse. So then one can assume that the rest of the data will be probably lying along the minimum, minor axis, these lines. So if I take this and that vectors, basis vectors, then basically they are normal to each other, major and minor axis of this. They form what is called the orthonormal basis. And so that is what we call the proper orthogonal modes, all right? So basically, if I project all these data points onto these two lines, then I have a set of data which capture most of the essential features of the entire data set. May not be fully represented, but okay. So that is a way to do it. You go back to the covariance matrix, and how you do it is actually, if you go back to linear algebra, first I have to find, there's a C matrix which I've already computed. I'm going to find the eigenvalues of the covariance matrix that we know how to do. Okay, for two-dimensional systems like this, you can do hand calculation and find the eigenvectors. But if this is a huge, then there are special algorithms for you to find. So now you diagonalize this C, okay, by this kind of transformation. And then the orthogonality, because these two are orthogonal to each other, they have a condition to be satisfied, okay? So you go and put all these matrices into this transformation, diagonalization. And when you do that, you diagonalize the covariance matrix into this form. This is the eigenvalues. And then I have everything there now. And to compute the variance along each principal axis, the data must be projected onto the eigenvectors. Okay, so if I look at these two axes, the data, if I take the original data set and project it into the major axis and the minor axis, okay, so this is the reduced data set. Okay, and if you look at different directions here, this is the basis vectors. If you look along the UA, of course, there is no correlation because along this axis, I only have UA. Along this, I only have UB. But everywhere else, I have a whole lot of others. So sometimes you can find that it is correlated and others not correlated. The meaning will become clear to you when you run some of the MATLAB code. So I'm not going to talk much about it. So the covariance matrix of the data projected on the POD basis, okay, if you do it, it will be like that. And basically you get the eigenvalues. So the covariance matrix of the data which is projected on the POD basis, that will be the eigen. And when you want to, after you calculate the eigenvalues, you have to arrange the eigenvalues. Eigenvalue matrix is a diagonal. The first element there, that should be the largest value, and the last one will be the smallest. So you order it like that. Okay, so now the original, so the largest eigenvalue will correspond to this, and based on this eigenvalue, you have total kinetic energy, which is given by that. Eigenvalues basically will help you. The percentage of kinetic energy for the first mode will be this one here, and the second mode is that. And for the given data set, you can find that the total KE is 4.96. The mode 1 contains about 78% of the total kinetic energy, and the remaining 22. So effectively, I can even forget about the blue data. All I need is this entire set of data can be represented along this measure, because it gives you close to 80% of the energy, and then proceed with whatever I am with the reduced data set. Okay, instead of all these things, I only deal the lines. So now the POD, if you look at this thing here, you do some transform. You want to find what is the reduced data set, the red and blue. So A is actually U times the eigenvector. So you put this stuff here and expand it out, and UA is actually U times the, and you can write A as phi minus phi inverse, and that is A phi transpose. Okay, so you go and do all these calculations, you end up with some big operations here. And I've deliberately taken out the red and blue, because the blue stuff here will correspond to this mode here on the blue line, and the red correspond to the red. So I split it out. I can rewrite this into two modes like that. Okay, so the first one here is U bar, I'm going to call it U bar 1, and the other one is U bar 2. So basically, your early data set is actually equivalent to this two. So U is this. So original fluctuations have been decomposed as a sum of contribution of two modes based on projection of the original data. So when you look at the general form of writing these pod modes, these are called POD modes. Its general form is this, and to understand what is the geometrical interpretation which you can do if the data is 2D, like only two data points there, but the values of the two data points vary over time, and you can see the geometrical interpretation is given here. If I have a data point here, this one will be the actual one. This is the projected one. Okay, this is the UA, and the other one is UB. This is the actual data at that point. This is the projected. They are different, but it's okay. This is the P, and this is your AK matrix here, distance. Okay, so you can actually represent the original field as the sum of all the modes. Okay, and maybe it's not necessary, because you will just keep the modes which have the highest energy content. Okay, so this way you have a smaller this thing. So how good it is, you can see. You calculated this POD modes, you go and combine. Red one is the first mode, the second mode, and the combined mode. And it looks like this is the original PIV data. they look almost the same. They're not exactly the same, but the behavior and the richness is captured to some extent, like the causes Stanford bunny. Okay, and this is good enough for initial calculation because the effort you spend in getting the necessary information is much lower than what you would if you use the high fidelity. So this is the key idea. Okay, it's a powerful method for large systems. Okay, so now you can repeat it. So I'm going to go very fast now because I can have many points. Okay, you repeat the process. At 305.80. So I will have. I only took 2, but if I take at 5805, then I will have 5,805 such signals coming from the 5805 spatial points in the view domain, and over 3,580 time instant. So this I can actually, snapshot metrics can be arranged for all this. You have going like this, the first snapshot, first column, and last column. So you have an array. Okay, so you can do all these things. So each row will hold the fluctuating velocity at 5,805 at a given time. Okay, so you need to assemble these matrices for you to do the same thing. You go and do, you compute the eigenvalues. Now your eigenvalues will be a lot more because the system is larger. So you need to use algorithm. You can't calculate by hand, and they're very efficient algorithms to do that. And then corresponding to the eigenvalues, you need to find the eigenvectors, and the eigenvectors are the port modes, and the eigenvectors will give you the estimate of the energy of the system. Okay, so you go and do all this, you will get the reduced order models here. Okay, so if you go and plot, okay, if I take there will be several modes. So what I do for multi-system is I'm going to plot the eigenvalue for each mode and the energy on this axis. So I know that corresponding to each, what is the total kinetic energy. So if you look at this, the first mode will give me close to like 20% of the energy. The second mode will give me about 8%, third, and so on. So there are about 10 modes here, and you can keep other modes as well, but they will be very small. Okay, so I don't need to keep all, I truncate. So that's how the truncation term, came about in one of the reduced order model. So here says I just take first mode here, second mode, and third mode, and then I see what is this, and then corresponding to this, you can plot the time signal. All right, everything is very clear, and then you can see from the contours whether this thing is like this is correlated, this is uncorrelated, and so on. The colors. Okay, it's all explained in the paper, and I hope you will read it and play with the MATLAB code to understand. So now you can also approximate the fluctuating velocity field using just mode 1, because that captures the highest. So I just represent the fluctuating velocity by the mode 1. So that makes my job a lot easier. And in order to make any sense, I have to add back my mean velocity, right? Because fluctuation contours alone is not. I want the total velocity field. So you add back this mode into the mean velocity, which you've already calculated before you began all this process, and then you can plot the contours at 4 instants of time, and you can see the development of the separation bubble region here. Okay, with at 4 instants of time, I'm able to capture essential features. I'm not going to do any measurement. I mean, from the measured data, you can construct as many fields as you want. Okay, so this is something like what you have seen. This is for the 2 points. You basically get a curve, right? Because you know how UA varies. But for a 2D field, you have to have contours because there are so many points. It's not just UA and UB, but so that's why you plot the contours of this. So this is what you see here is the equivalent of this one. Okay, so the pod Okay, there are two approaches. Okay, so what you have seen earlier, I mean, what I've been talking about, that's a direct port. Okay, so this direct port is you're viewing it as a deterministic spatial modes and random time coefficients. Okay, but you can also look at it the other way. You can look at it as deterministic temporal modes and random spatial coefficient. And this is the approach which is very popular among CFD people. So I will take at different time snapshots, I take the flow field, okay? And then I compute the code modes and so on. Okay, so same thing here. So here, what you do for that, that is called a snapshot mode, and that was introduced in 1987 by a person called Sirovich, and that kind of motivated a lot of activities of applying snapshot PODs in fluid mechanics and various other areas. Because so I think in view of the limited time, I do not want to spend a lot of time on this. But again, you just have to rearrange the thing. You could actually switch x with t because, this, if you look at this function here, this symmetric. It doesn't really matter whether if I switch t with x, you still get, you can use this approach, okay? But we rather use this one, the Sirovich snapshot. So you have to rearrange now because now your covariance matrix is now in terms of nt. And n is the number of spatial velocities in each field. M is the total number of velocity fields. So you go and do all these things, compute eigenvalues, everything. The eigenvectors corresponding to this snapshot POD eigenvalues I've labeled subscript S. Okay, so you go and find, you will get the POD, snapshot POD. Okay, you find that the snapshot POD has less storage requirements and is faster than the direct POD. So, like for example, for the same data set, if you use snapshot POD, my covariance matrix will only have 12.8 million elements. If I use the standard direct POD, it will have 33.7. Okay, so now you can add other things. You can add so far we only look at longitudinal. You can add the Y component, Z component, then the matrix will become even larger. Okay, it goes on like this. Okay, so in such a case, when you take on more values, like say 2D problem, including U and V, then your covariant matrix coming from the direct POD will have 135 times 10 to the power of 6 elements, but the covariant matrix coming from the snapshot PhD will have the same as before. So that is the beauty of Sirovich's contribution to this field. And snapshot POD is what it has less storage requirements and is faster than the direct POD, and that is what we always use. The direct POD is used for measurements with limited sensor location. Say like that experimental apparatus I've shown you, if you're measuring, say, pressure sensors on the top, I won't be able to put a lot of pressure sensors, but I will put a few. And then based on that data, I will use direct POD to construct. Okay, so the snapshot PhD is what is not just dependent on space and time, but I can do for a lot of things. Like for example, if I have aerodynamic solver, I can compute the flow field for different Mach numbers, get lift coefficient, get a pressure field. Okay, with this data, I can actually compute a low dimensional POD model and get a port coefficient, and then I can reconstruct my flow field, okay, using the port modes. Okay, so this is what is happening. The POD is strongly connected to what is called the SVD, the singular value decomposition. It's a very popular method in many fields. The idea was there many years ago because when people were developing the matrix methods and all that, decomposition, matrix decompositions, very important for various things. But the person who really put this SBD into practical mode is the founder of MATLAB, Cliff Moller, right? And here's a movie here which he gave a talk in October last year during COVID-19. It's called SVD Saves the World. And if you have time, you can click on this link and he will tell you the story of SVD. So SVD basically of a matrix is this one here. And this can be closely related to the pod. And I've given you some slides here to do that. So I'm not going to talk so much about it because part of the learning is actually coming from doing instead of listening to your lecturers and so on. Okay, so we'll give you some idea and then you do it. So here, this is the snapshot POD. You get the U data. After you arrange all this in columns, and then the SVD. You take a SVD of that matrix. Okay, and then you can get pod modes and so on. So if you read the remaining paragraphs or sections of the paper by Professor Weiss, he will show you the connection between the direct POD and the snapshot PAD and the SPD. So that I leave it as a reading assignment and doing assignment to you. Now, of late, people have put together a platform called PyMore. These are all model order reduction routines written in Python. And this is something which Dr. Madhukar and I are thinking about dabbling in and maybe offer some courses or whatever in the future, because we believe that this has an important role to play in machine learning and the application of this in fluid dynamics. Okay, so this is to prepare young people in the audience that don't just do computational fluid dynamics. Okay, that is okay, but think a little bit more than what is possible, because you'll be living in a world where this kind of things are going to happen. That's all I have to say.
Sir, can you share that link in the chat?
I will.
Python.
The link, yeah, sure. I will give you the link. Okay, let me go to the. Okay, I'll give you.
Yes, sir.
Yeah, I'll give you just a minute. Yeah. Okay, this one here. Okay, right. I'm going to send you now. Now I have to go back. Okay, where? How do I message? Right there.
There is a chat box, chat option.
Chat box. I have to find out, man. I'm not very familiar with this Google Meet.
So just a top corner, you see the
I see raise hand.
three lines.
Three dots.
Three lines.
Three
Top corner.
Three dots in it. More options.
If you put a cursor on that, you will see that chat with everyone.
Oh, this one. Okay,
Go
okay.
to the top.
Okay. I got it. Okay. You got it?
Yeah.
You see it?
Yeah.
Okay. And let me also send you the link to the SVD Conquers the World, okay, which is a very entertaining talk. And I would like you to look into it. Okay, so that is Steve Mahler's copy. All right. Where is that fellow again? It's not showing him. Oh, chat. Okay, here. Paste. Okay. And then one more on PyMore, which I hope you guys can take a look, because PyMore links. Okay, these are the three main things there for you guys. Okay. Okay, that's all. So I think it's lunchtime in India, right?
Yeah.
Thanks very much, Dr. Murali. That was a very nice.
Yeah. So I'll see you again after the lunch, where I would like to introduce you to some ideas of machine learning, and then thereafter Professor Madhukar will take it up and show you case studies and so on.
But do we have time for a
Yeah. Please, yeah.
Okay, Murali, that was a very nice talk. I just loved it very much. Thank you. It strikes me that the eigenvectors, the POD modes, will still be quite long vectors to carry around. Do you think there is any possibility of compressing them still further using neural?
Yeah. That's a very good question. You see, this is just one approach, but there are a lot of other approaches where you can actually project the POD. You can project the differential equations. The physical PDEs of the processes onto the chord space, the reduced space. Okay, so that is another approach. That will give you the Galerkin pod and things like that. Which is quite popular with many people. So there are many methods to do it. True, as the size of the problem goes, size of your data grows, yes, the number of columns in that correlation matrix will become large, storage and so on. But one benefit you can see how you interpret it. Like, for example, if you look at the snapshot, then the size is controlled, So that is something, which you cannot run away from, because you really want some level of fidelity in your low order model. So if you take away too much of the data, then you don't get that much of fidelity. That's what I feel. But yes, this is a point. And this is something which we can look at, flow visualization, 3D data is very huge, right?
Yes.
I guess you can apply pod to have a faster visualization of flow fields, by reconstructing and so on.
Yes.
Because a lot of the time you do the computation on a high performance computer and then you're visualizing it on a low performance workstation, and then that has a lot of issues with memory and so on. So while you can just maybe reduce the, apply a reduced order modeling on the data set and visualize that.
Dr. Murali, I wanted to know if for transient problems, is there anyone, is POD better than, say, DMD, dynamic mode decomposition, or?
Oh yeah, yeah. Those are some of the things that people use: dynamic mode decomposition, DIEM, ERA, and so on. In fact, my students and I have explored some of these, and I will talk about some of it in the next talk on machine learning. Okay.
Okay, thank you.
Yeah, not so much, but to talk about all this in detail, you really need a short course, in my view, on Redis Automa, because there are so many developments. Okay, and there are many groups developing a lot of things in this area, and it's time to actually, I feel, to put together something, and train the next generation to give them a new view of modeling.
Thank you.
Yeah. All done?
So, any questions? Yeah, there is one. Yeah.
Yeah. Thank you, Professor Murali, for such a nice talk and giving some thought process for looking beyond CFD and current state of the art about methods that may be used for getting a faster solution and with the reasonable accuracy. I hope, Professor Dirigude, this talks or PPT will be shared with the participants so that we can spend more time for understanding the thought process.
Yeah, PPTs right now I haven't collected from any participant, but I'm recording the videos. So once I edit the recordings, maybe I'll make it open.
Okay, okay. Thank you, Professor Murali.
that
I
will
need
be
some time to understand these methods, but really it was a nice talk, and that has simulated some thought process inside us.
Yeah, thank you. That was my intention. I mean, how to best bring this concept in a very easy manner, because you try to read it in the open literature, it is going to be very difficult for you to really appreciate it. So I think with this paper by the Professor Weiss in TU Berlin, and also the associated MATLAB codes and data sets he has given in his paper, and that will be a good start for many of you to start playing around with. And if you have any question, you can always send me an email or something, and I'm willing to engage you guys. Okay.
Yeah, thank you so much. At this time, I'm not in a position to ask any question, but certainly there will be doubts when we go through the papers and think about it.
Yeah. Yeah. Okay.
Okay, so thank you, Dr. Murali.
Yes. Thank you very much. I'll see you in an hour's time. Huh?
Yeah, now we'll stop this part of the session and we'll meet at 2 o'clock.
Okay.
Thank you all participants.
All right. Okay.